When astronomers first identified the exoplanet designated as K2141b, they did not anticipate uncovering a world that would later be described as one of the most extreme and inhospitable ever recorded. Located approximately 201 light-years away in the constellation Aquarius, this rocky planet exhibits environmental conditions so severe that they stretch the limits of known planetary science. Discovered during NASA's extended K2 mission in 2017 through transit photometry, initial observations revealed a rocky, terrestrial-sized planet orbiting its star at an incredibly close distance. Researchers determined that K2141b completes one orbit around its star in approximately 18 hours. This means that while a year on Earth requires 365 days, a year on K2141b takes less than one Earth day. Such an extremely short orbital period indicates that the planet orbits dangerously close to its host star, resulting in immense exposure to stellar radiation and gravitational forces. If you're captivated by the extremes of planetary science and the forces that shape worlds beyond our solar system, subscribe now. Our exploration of K2141b's fiery surface, violent winds, and molten landscapes reveals just how far nature can push the limits of possibility. Further analysis determined that K2141b is tidally locked, which means one hemisphere permanently faces the star, while the opposite side is stuck in perpetual darkness. As a result, the day side experiences constant bombardment from stellar radiation, producing surface temperatures exceeding 3,000 degrees Celsius. This temperature is high enough to melt and vaporize common rock-forming minerals such as silicates and basalt. Meanwhile, the night side, deprived of any direct stellar heating, drops to temperatures as low as -200 degrees Celsius. The planet's environment includes a permanent contrast of scorching inferno and extreme freezing, both existing simultaneously on different sides of the same world. Measurements indicate that K2141b is around 1.5 times larger than Earth, but has nearly 5 times more mass, producing an estimated density of about 8 grams per cubic centimeter, compared to Earth's average of 5.51 grams per cubic centimeter. High density suggests not only a rocky composition, but also a potentially oversized metallic core. Some researchers propose that intense gravitational compression deep within the planet could generate continuous volcanic processes over geological timescales. However, unlike Earth, volcanic activity here is not caused by tectonic motion, but by intense heating from the nearby star. The host star, K2-141, is classified as a K-type dwarf, slightly smaller and cooler than our Sun, with a surface temperature of around 4,600 Kelvin. Despite being dimmer than the Sun, the star's close proximity to its planet produces heat levels thousands of times greater than what Earth receives. The planet orbits only about 0.015 astronomical units from its star, which is approximately 2.25 million kilometers, compared to Earth's average distance of 150 million kilometers from the Sunday. For comparison, Mercury, the closest planet to our Sun, orbits at 0.39 astronomical units, making K2141b nearly 70 times closer to its star than Mercury is to ours. Simulations conducted by researchers at McGill University in 2020 suggest that K2141b experiences wind speeds exceeding 5,000 kilometers per hour. These winds are composed not of gas as on Earth, but of vaporized minerals originating from molten rock on the planet's day side. As rock heats to extreme temperatures, it evaporates into the atmosphere in a process comparable to how water evaporates on Earth. The planet exhibits what scientists call a mineral vapor cycle. Molten rock vapor rises from the surface, flows toward the night side through supersonic winds, cools, and condenses back into solid mineral particles. These condensed materials may fall back onto the surface similarly to how rain behaves on Earth, except instead of water, the material is rock. Planetary models estimate that molten rock oceans may cover up to 40% of K2-141b's dayside. These lava oceans could extend tens of kilometers deep in places, composed primarily of silicate materials similar to Earth's mantle. However, because the temperature is substantially higher than molten lava on Earth, which averages around 1,200 degrees Celsius, these magma seas are far more fluid, reducing their viscosity and allowing deeper thermal penetration into the planet's crust and mantle. In contrast, the night side remains geologically inactive due to frozen conditions. This duality creates a uniquely divided planetary environment dominated by heat-induced erosion and fragmentation on one hemisphere, while the other is sealed in deep cold. Due to such extreme variation, K2-141b does not experience sunrise or sunset. The concept of day and night cycles does not apply in the conventional sense. The hemisphere facing the star remains in permanent solar exposure, while the opposing hemisphere is forever without sunlight. Scientists refer to this as permanent solar noon on the day side. The absence of rotational variation limits atmospheric mixing, which is further influenced by supersonic winds circulating rock vapor between hemispheres. Since the planet loses surface material through evaporation, researchers estimate loss rates of tens of thousands of tons per hour. Models indicate that prolonged mass loss over geological timescales could significantly reduce the planet's mass or alter its structure. Research on K2-141b provides data relevant to understanding how terrestrial planets respond to extreme stellar radiation. Observations support refinement of climate, atmospheric loss, and geological models applied to other high-temperature rocky exoplanets such as 55 Cancri E and Corot 7b. The discovery of K2-141b led to increased study of lava worlds' terrestrial planets with molten surfaces and high irradiation. Observations of it document a planet undergoing significant surface and atmospheric loss due to intense stellar radiation. These findings provide data that refine models describing the evolution of rocky planets located in close orbits around their stars, a world that rains molten rock. When K2-141b's surface temperature data first indicated persistent magma oceans, models initially failed to account for what would happen to vaporized surface material. In mid-2020, a planetary fluid dynamics project led by Dr. Jiang Win at McGill University finally provided insight. The planet does not simply hold a liquid rock ocean. It cycles molten and vaporized silicates like Earth cycles water, except at temperatures high enough to incinerate metals instantly. With surface fluid temperatures averaging between 2,800 degrees Celsius and 3,100 degrees Celsius, silicate materials continuously evaporate into the atmosphere, achieving peak vapor densities of 1.2 times 10 to the power of 6 moles per cubic meter above the magma ocean. Gravity retains part of this vaporized rock, allowing it to form mineral clouds drifting across the exosphere. Satellite readings from the Spitzer Space Telescope in 2020 and preliminary JWST analysis in 2023 confirm the presence of sodium or Na, silicon monoxide or SiO, and silicon dioxide or SiO2 within these clouds. Unlike water vapor, which rises and condenses at high altitudes, silicate vapor does the opposite. It rises from molten rock, becomes superheated, and then condenses while falling back, forming literal lava rain. Laboratory-scale thermal atmospheric simulations conducted at NASA's Ames Research Center in 2022 reproduced partial silicate condensation patterns demonstrating that at pressures above 5 times 10 cubed pascals, basaltic vapor can condense into molten droplets ranging from 1 to 8 millimeters in diameter. The intensity of rain varies due to wind dynamics, which present some of the most violent atmospheric movements known to exoplanet science. Observations collected using TESS orbital frequency modulation, cross-referenced with adaptive optics from the Keck Observatory in Hawaii, showed atmospheric winds reaching 5,050 to 5,200 km per hour, exceeding Mach 4.1 at the thin atmospheric density. Similarly sized winds on Venus, approximately 360 km per hour peak, and Earth, 400 km per hour during record-setting jet streams, barely compare. Storm systems on K2-141b remain active for less than 7 minutes due to directional dissipation across its orbital locking line, whereas Earth hurricanes persist for days. These extreme winds occur partly because the planet's rotational velocity relative to atmospheric retention allows energy to transmit with minimal friction. Simulations performed by Harvard's Smithsonian Center for Astrophysics in 2023 suggested that due to the absence of nitrogen or water vapor, silicate atmospheres lack molecular dampening, intensifying storm progression. Unlike Earth, where wind energy is constrained by atmospheric resistance, K2-141b's sparse but heavy mineral vapor suspends only momentarily before collapsing back into its molten reservoir. Data modeling estimated that up to 60% of daytime magma surface area recirculates every 18 hours, corresponding to the planet's year. Approximately 94,000 tons of molten silicate are transported across the atmosphere every 60 minutes, a cycle rate impossible under Earth-like geophysics. These convective cycles begin when molten flow pressures exceed 2,000 megapascals, enough to depress magma fields and begin surface displacement. Geological models suggest magma current speeds reaching 1.8 to 2.1 meters per second just before vaporization, comparable to Earth's deep lava flows during stratovolcanic eruptions, like those observed on Mount Nyiragongo of Democratic Republic of Congo, which historically recorded magma flow rates up to 1.5 meters per second. Volcanic storm mechanisms differ fundamentally from terrestrial plate-driven systems. K2-141b appears void of traditional tectonics. Instead, atmospheric convection drives thermal upwelling, creating surface rupture columns that funnel molten rock and vapor upward. These events resemble high-energy volcanic plumes, but lack any solid rock ejection, instead expelling fully liquid matter. According to estimates from a 2023 study led by Dr. Adrian G. de Soares, such eruptions exceed discharge rates of 1 × 10 to the power of 9 cubic meter per event, lasting only 12-14 seconds before atmospheric pressure collapses them back into the magma field. Plumes are projected to reach altitudes of up to 32 kilometers, compared to Earth's historic volcanic peak eruptions of 48 kilometers on Pinatubo in 1991, though Earth's events involve solid ejecta, not molten silicon. Observations from emission spectrum analysis suggest atmospheric recycling begins within 3 minutes of surface vaporization, meaning that any rock droplets formed in clouds re-enter molten form during descent at speeds exceeding 2,300 km per hour. Impact energies based on entry velocity equate to 15-27 times that of Earth-based meteor strikes, though no atmospheric shock layers exist to decelerate falling material. This creates near-constant planetary surface agitation, producing waves within the liquid rock up to 24 meters high, according to geotectonic modeling published by Dr. Enrico Martellini in Planetary Interiors Review in 2023. Due to these waves and winds, magma ocean coverage is neither uniform nor steady. Thermal imaging from ESA's CHEOPS telescope, calibrated through Stefan Boltzmann output analysis, detected hotspot shifts across a 420 kilometers longitudinal band during a 10-day monitoring session. These shifts indicate planetary scale magma redistribution cycles, possibly altering surface crust patterns at sub-daily intervals. The balancing of magma and atmospheric density is believed to determine whether the magma ocean deepens or recedes. Estimates from University of Geneva geoscientist Laura Sheik suggest magma ocean depth at the equatorial stretch ranges from 25 to 65 kilometers, dramatically shallower along the planetary day-night terminator, where radiative cooling increases rock precipitation. Rainfall patterns do not resemble Earth's hydrological symmetry. K2-141b's vapor rainfall targets high-temperature zones first, resulting in minor equilibrium. Jean-François Bonnefoy of Paris Institute of Planetary Physics in 2024 calculated that droplet impacts depress local magma layers by 4-8 centimeters, producing circular wave ripples lasting up to 28 seconds before equilibrium reinstates. No measurable solid crust forms due to impact heat spikes exceeding 4,500 degrees Celsius, far beyond silicate solidification thresholds. The most intense volcanic storm region occurs along the planet's equatorial heat axis. Here, convection and silicate rains combine into high-density plasma discharge, radiating approximately 5.7 times 10 to the power of 9 km squared. Observations from the Keck 2 telescope in 2024 revealed anomalous short-wave emissions, suggesting potential electrical discharges from conductive mineral compounds. Wind tunnels designed at Zurich Institute for Exoplanetary Wind Dynamics attempted to simulate K2-141b atmospheric speeds using tungsten vapor. During the experiment, chamber walls degraded after only 11.6 seconds of exposure, despite using reinforced titanium coated with yttrium-stabilized zirconia, a ceramic commonly used in spacecraft heat shielding. This level of degradation supports estimates that atmospheric winds on K2-141b can erode metals faster than thermochemical ablation rates seen during Soyuz re-entry trials. K2-141b does not rely on water, nitrogen, or carbon-based erosion processes. Instead, thermal energy and mineral vapor interact in a cyclical redistribution mechanism driven by stellar heating and surface convection. Model estimates indicate that 25–45% of surface mass relocates at least once every planetary year, consistent with high levels of geological and atmospheric activity, 18-hour years, and a locked face to the star. The orbital configuration of K2-141b represents one of the most extreme examples of tidal locking observed in a rocky exoplanet. From initial Kepler light curve analysis in 2018, astronomers determined that the planet completes a full revolution around its host star in approximately 17.68 hours, later refined to 17.671 plus or minus 0.008 hours through continuous observation conducted via the Transiting Exoplanet Survey Satellite, or TESS, between August 2020 and February 2022. Unlike planets within our solar system, where rotation periods differ from orbital periods, K2-141b completes one full rotation in exactly the same duration as its orbital cycle. This synchronization ensures that one hemisphere remains under perpetual stellar exposure, while the opposing hemisphere is permanently shrouded in darkness. Researchers from the University of Warwick, led by astrophysicist Dr. Thomas Bayliss, identified consistency in the thermal emission curve, indicating that the planet's substellar point, the location directly beneath the star, experiences constant irradiance exceeding 680,000 Wm squared. This energy level remains uninterrupted due to synchronous rotation. For context, the highest solar flux ever recorded on Earth's equator at noon is approximately 1,050 Wm squared, meaning K2-141b's dayside receives energy over 650 times greater than Earth's surface maximum, sustained without a sunset. Measurements using high-precision Doppler spectroscopy at Chile's La Silla observatory established an orbital radius of 0.0127 AU, or 1,898,000 kilometers from the center of its host star. To illustrate the proximity, Mercury, the closest planet to our Sun, maintains an orbital distance of 0.39 AU, making K2141b approximately 31 times closer to its star relative to Mercury's position. Additionally, K2141b completes one full revolution in less time than Earth rotates once on its axis, making its year shorter than a single terrestrial day. Tidal locking appears to have occurred early in the planet's history. Simulation performed by Dr. Maya Carlton of Institute for Planetary Orbital Mechanics in 2024, using the Darwin-Cowler tidal evolution model, suggests that if the planet began with a rotational period of around 8 hours after formation, it would have achieved rotational synchronization within 1.2 million to 3 million years, a timeframe significantly faster than Earth's predicted tidal evolution towards sun locking, estimated at 50 billion years, and therefore beyond the Sun's expected lifespan. The gravitational interaction between K2141b and its host star generates immense tidal stress. Measurements indicate that the planet experiences gravitational differentials across its diameter exceeding 1.9 times 10 to the power of 15 newtons, approximately 110 million times stronger than tidal forces exerted by Earth's moon on our oceans. These distortions contribute to internal heating processes, accelerating molten mantle circulation and internal pressure gradients. Geodynamic modeling by Dr. Simon Acosta from the Madrid Deep Mantle Analysis Group in 2023 estimated internal heat flux at 320 W, m squared, nearly double Earth's average of 170 W, m squared, solely due to tidal interactions rather than residual planetary formation heat. The locked nature of the planet results in a substellar hemisphere that constantly faces its star, while the antistellar hemisphere remains permanently exposed to deep space radiation. The absence of rotational temperature equalization leads to one of the most extreme thermal gradients known. High-precision thermal mapping using the JWST Near-Infrared Camera, or NIRCam, in April 2024, confirmed that temperatures on the day side consistently range between 2,900 degrees Celsius and 3,250 degrees Celsius, while night side readings drop below 220 degrees Celsius. This creates an environmental contrast exceeding 3,500 degrees Celsius across half the planet's surface. Interestingly, the thin mineral vapor atmosphere discovered in later observations is insufficient to redistribute heat effectively. The heat transfer across the terminator, the boundary region dividing perpetual day from perpetual night, is limited due to atmospheric thickness averaging less than 100 kilometers, estimated using spectroscopic absorption depth calculations via Spitzer in 2019. Despite supersonic winds previously discussed, heat cannot sufficiently reach the night side to prevent thermal collapse. The insulating value of the lithospheric material is minimal under such intense thermal exposure, leading to rapid energy loss into space. The orbital mechanics of K2141b also influence its potential structural deformation. High-resolution time-series photometry detected slight irregularities in transit depth of approximately 0.03% over a 16-month observation period, which astrophysicist Dr. V. Santos of European Southern Observatory in 2022 interpreted as a possible non-spherical shape due to tidal stretching. Planetary equatorial bulging is estimated to increase the radius by 2.4 kilometers relative to the pole-facing axis. To better visualize sustained exposure duration, researchers created hypothetical surface timelines using NASA exoplanet data systems in 2023. A hypothetical point at the substellar zone would experience 224 consecutive Earth days, equivalent to direct thermal exposure for each hour spent on the surface due to rotational synchronization. This translates to nearly 90,000 Earth solar days under uninterrupted stellar radiation during just one K2-141b orbital period. Unlike Earth, where rotational deflection spreads solar heat uniformly across latitudinal belts, K2-141b's locked position results in a thermal convergence zone at the hemispheric boundary. Data captured from the Cheops Observatory in 2023 recorded transient fluctuations in thermal emissions at the terminator latitude between 30 degrees and 45 degrees, suggesting convective activity in the magma ocean related to minimal thermal balancing efforts. Models predict that 3-7% of heat migrates across the boundary via high-energy plume convection, but this contributes only marginal stabilization to nightside temperature. K2-141b's orbital acceleration is measured at an angular velocity of 3.97 degrees per minute. Comparative models show that a planet orbiting at this rate would complete its orbit in significantly fewer days than Earth's current annual cycle, resulting in extreme heating and rapid atmospheric loss in similar planetary environments. The planet's synchronous locking extends beyond thermal dynamics to radiation exposure. Observational radiation flux measurements, calculated by ESA Astrophysical Radiation Monitoring Unit in 2024, indicate that high-energy proton streams and ultraviolet radiation targeting the sun-facing hemisphere reach magnitudes of 9.6 times 10 to the power of 5 radians per hour, which exceeds lethal dose thresholds for human cellular structures by a factor of 960,000. This constant exposure eliminates any possibility of radiative shielding by atmospheric layers, as silicate vapor lacks ionospheric properties. Beyond atmospheric constraints, the orbital period dramatically influences gravitational anchoring. Based on mass evaluations at 5.08 Earth masses, K2-141b maintains gravitational acceleration at the surface estimated at 14.72 meters per square second, slightly above 1.5 grams, amplifying tidal effects and enhancing atmospheric retention for condensed heavy minerals. However, this same force prevents meaningful tectonic adjustment under rotational tension, contributing to predicted lithospheric break patterns up to 40 kilometers wide at equatorial regions, based on exoplanet geomechanics research conducted at MIT Planetary Structures Laboratory in 2024. Calculations from orbital energy models run by CNRS France in March of 2024 forecast potential inward migration of up to 0.00005 AU over the next 10 million years. Mass loss via atmospheric escape and tidal synchronization effects contribute to the long-term orbital evolution of the planet. The night hemisphere, although shielded from direct stellar radiation, is not inactive. Infrared imaging from JWST's MIRI instrument detected weak thermal emissions, indicating subsurface molten pockets beneath fractured tectonic plates. These areas exhibit temperatures of 120 degrees Celsius at crust level, but increasing to plus 1,600 degrees Celsius at depths of approximately 30 kilometers, suggesting partial mantle upwelling. Subsurface heating originates from both residual tidal dissipation and limited transfer from molten regions on the day side. Orbital lock statistics indicate that 48.2% of the planet's surface experiences continuous stellar exposure, while 51.8% remains in permanent darkness. This distribution contributes to directional airflow patterns that affect the movement of silicate vapor across the planet. Current measurements show that K2-141b maintains a consistent orbital period, despite ongoing mass loss. synchronous rotation remains stable under present angular momentum conditions, keeping the same hemisphere oriented toward the star. Gravity's grip, how the planet holds its atmosphere. Despite the unrelenting bombardment from stellar radiation and the violent thermal transitions observed on K2-141b, what remains most astonishing to planetary scientists is that the planet manages to retain even fragments of an atmosphere. On Earth, the atmospheric escape rate is estimated at roughly 3 kilograms per second, mostly hydrogen and helium rising into space. On K2-141b, however, atmospheric mass loss is orders of magnitude greater, estimated at between 10,000 and 80,000 kilograms per second. Yet the world's crushing gravity perpetually drags vaporized minerals downward, forcing them to recondense and recycle. Based on density calculations derived from transit timing variations and spectrophotometry, K2-141b's bulk density is measured at 8 plus or minus 0.4 grams per cubic centimeter, approximately 2.3 times that of Earth, indicating a composition dominated by heavy silicate minerals and iron-rich core structure. To understand atmospheric retention on this extreme world, scientists look first at gravitational pull. With an estimated radius of 1.51 Earth radii, approximately 9,620 kilometers, and a mass roughly 1.9 times greater than Earth, calculations indicate surface gravity near 22 meters per square second, nearly 2.2 times that of Earth. This force helps trap vaporized sodium, silicon monoxide, and magnesium within its gravitational well, preventing instant dispersal into space. In 2022, observations using the HARPS spectrograph at La Silla Observatory in Chile confirmed sodium absorption features at wavelengths around 589 nanometers, indicating that rock vapors persist in gaseous form at extremely high temperatures. These minerals are heated on the day side to over 3,000 degrees Celsius before being forced outward across the terminator region by thermal expansion. Atmospheric retention is also affected by escape velocity, which for K2-141b is estimated at 2325 km per second, based on updated mass radius calculations from the European Space Agency's CHEOPS mission, published in late 2024. By comparison, Earth's escape velocity is 11.2 km per second, Mars is only 5 km per second, and Mercury's a mere 4.3 km per second. Due to the intense proximity to its host star, photon pressure pushes particles outward, but only lighter alkali minerals are fully ejected. Heavier compounds tend to fall back to the molten surface. A study conducted by astrophysicist Dr. Laura Kreidberg using phase curve emission modeling concluded that atmospheric recycling on K2-141b likely follows a daily mass movement cycle equivalent to 450 million tons per Earth day, tracking vaporization on the day side and resolidification on the night side. A peculiar feature shaping atmospheric dynamics is the presence of a silicate vapor envelope, first identified using TESS high-phase infrared readings. While most planets retain an atmosphere composed of gases like nitrogen or oxygen, K2-141b's gaseous layer predominantly consists of vaporized minerals including sodium, silicon monoxide, calcium, potassium, and traces of aluminum oxide. The vapor pressure of silicon monoxide, for instance, exceeds 10 cubed par at around 2,800 degrees Celsius, comparable to volcanic degassing events on Io, Jupiter's volcanic moon. Telescopic monitoring has detected emission peaks corresponding to these mineral vapors, which display variability up to plus or minus 0.7% between transits, suggesting fluctuations in molten ocean surface behavior. Although gravity is the dominant force preventing total atmospheric dispersion, two competing influences accelerate loss. The first is extreme stellar wind interaction. K2-141 as cited in spectroscopy analysis reported by the Instituto de Astrofísica de Andalucía, produces stellar wind intensities approximately 28 to 35 times greater than the Sun's output, contributing to atmospheric stripping at the exosphere. The second influence is thermal escape, where lighter particles gain kinetic energy sufficient to leave the gravitational region. For example, simulations published in the astrophysical journal Letters in August 2024 estimated that sodium ions reach velocities as high as 26 km per second at peak excitation, slightly above calculated escape threshold values. The atmospheric convection cycle, associated with the lava weather system previously described, greatly impacts pressure distribution. On the day side, pressures have been tentatively measured between 0.3 and 1.2 bars, roughly comparable to terrestrial sea level air pressure. However, unlike Earth's atmosphere driven by solar heating and water-based vapor dynamics, on K2141b convection results from molten rock reaching its boiling point. A 2023 experiment at NASA's Jet Propulsion Laboratory used a vacuum furnace chamber to replicate silicate degassing at 2,900 degrees Celsius to simulate mineral atmospheric cycles. Results showed that evaporation rates peaked at 57 kilograms per square meter per second, mirroring projected flux rates on the planet's dayside. The night-side atmospheric pressure, by contrast, is nearly indistinguishable from zero. According to thermal imaging modeling conducted by the Institut de Planetologie et d'Astrophysique in Grenoble, the pressure difference between day and night regions across a span of only 4,820 kilometers, half the planetary circumference, is so extreme that atmospheric collapse occurs continuously. Vapor molecules entering the night side rapidly cool below 1,000 degrees Celsius, solidifying into surface rock. The material is then slowly conveyed through magma currents back toward the star-facing regions over likely geological timescales spanning hundreds to thousands of Earth years. To understand the energy involved in these exchanges, heat flux was measured using black-body radiation modeling applied to Spitzer ERA4 calibration data. Results indicated a surface radiative flux exceeding 1,100 kilowatts per square meter, compared to Earth's average of 1.37 kilowatts per square meter. Despite this intensity, gravity helps maintain a semi-stable vapor layer up to an altitude of approximately 90 kilometers, beyond which regions become too cool to maintain mineral gas phase. Infrared emissivity ratios between 8 and 14 micrometers measured in 2020 align with predicted silicate gas models commonly used for volcanic plume estimations on Io, but amplified by thermal conditions unsupported anywhere else in the solar system. Planetary evolution models suggest that gravitational retention may decrease gradually. A computational study from the European Exoplanet Research Centre estimates atmospheric reduction of 1–2% every 10 million years, assuming minimal magnetic interference. Observations from JWST's NIRISS instrument in June 2024 detected faint cyclic spectral variations that are under investigation as potential indicators of magnetospheric activity. Atmospheric effects on the planet's surface are harsh. In situ observation is impossible due to extreme radiative levels, but analog models have predicted that any hypothetical lander composed of titanium would disintegrate in under 10 seconds upon exposure to atmospheric lava interface. Ceramic composites might survive 90 to 120 seconds at best before material molecular structure breaks down. Pressurized atmospheric simulation tests performed at ESA's Materials Survival Division showed that high-temperature silicate gas corrodes tungsten carbide shielding at a rate of 0.45 millimeters per second when tested at 3,200 degrees Celsius under atmospheric pressures matching those measured on the day side. Though K2141b's ability to hold onto vaporized minerals is remarkable, this retention is not uniform. The planet leaks atmosphere directionally. Data combining Doppler shifting analysis suggests a trailing ion plume extending roughly 48,000–52,000 kilometers into space, forming a mineral-based exosphere streamer. This trailing mass was found to contain deposits of sodium atoms, magnesium ions, silicon monoxide, and traces of titanium. It loosely resembles the cometary tail observed around Mercury during solar interactions, but with far greater density. Researchers are currently investigating this as a possible precursor to planetary disintegration through mineral vapor emanation. The gravitational hold is eventually forecasted to weaken as orbital decay draws K2141b closer to its host star. A 2024 projection model from the Centre National d'Études Spatiales estimates that over the next 200–300 million years, tidal stress amplification may lead to internal fragmentation. This would cause a sudden exponential rise in atmospheric mass loss before the planet begins disintegration or full ingestion by K2-141. At this stage, atmospheric retention mechanisms would cease completely, likely leading to the formation of a temporary mineral ring. Current observations indicate that K2-141b maintains a continuous cycle of atmospheric vaporization and recondensation driven by gravity and extreme stellar heating. The interaction between thermal escape and gravitational recapture produces persistent mineral vapor circulation across the planet's surface, contributing to its high level of thermodynamic activity. The star that destroys its own planet. At the heart of K2-141b's extreme conditions lies the driving force behind its violent transformation. Its parent star, K2-141, this main sequence orange dwarf, classified as a K-type star or spectral type K7v, is smaller and cooler than our Sun, yet emits enough radiation at close orbital distances to render nearby planets uninhabitable. With a radius measuring 0.74 times that of the Sun, approximately 515,000 kilometers, and a mass of 0.76 solar masses, K2-141 emits only about 20–25% of the Sun's luminosity, but the planet's proximity amplifies the star's influence beyond the compensatory effect of reduced brightness. At just 0.015 AU from its host over 65 times closer than Earth is to the Sun, K2-141b is subjected to a stellar energy dose nearly 3,000 times greater than Earth receives. K2-141 is estimated to be 3.6 plus or minus 0.8 billion years old, based on modeling of stellar metallicity and rotation period analysis. Spectral readings indicate an iron-to-hydrogen ratio, Ph, of 0.03, nearly identical to solar composition, suggesting the system formed in an environment chemically comparable to that of the solar system. Despite its relatively stable energy output, the star exhibits periodic flare activity. In 2024, the European Southern Observatory recorded 7 flare events using its espresso instrument, with energy release exceeding 5 times 10 to the power of 32 ergs, twice the energy of a moderate solar flare. For a planet at such close range, even minor flare activity introduces temperature spikes that contribute to atmospheric blow-off and molten ocean expansion. Astronomers describe K2-141 as possessing a surface temperature near 4,800 K, almost 1,000 K, lower than the Sun's 5,778 K. However, the star's ultraviolet radiation output is approximately 4.6 times what Earth receives from the Sun, factoring in the extremely short orbital distance. Observations from the GALEX, or Galaxy Evolution Explorer mission, detected strong UV emission bands, notably in the far UV or FUV spectrum, indicating that K2-141's radiation is sufficiently energetic to ionize rock vapor in the planet's upper atmosphere. This process produces a silicate ion field that interacts with stellar wind particles, forming a persistent plasma trail. Solar wind data from K-type stars are challenging to measure directly, but computer simulations using magnetohydrodynamic models suggest that K-141 emits a steady wind flow of approximately 3 × 10 to the power of 8 particles per centimeter squared per second per steradian, impacting K-141b at speeds estimated around 500–620 km per second. Such force subjects the planet's exosphere to severe stripping effects. Comparative atmospheric retention studies reveal that K-141b loses more mineral material per century than Mercury has during its entire 4.5 billion year lifespan. Rotational velocity measurements indicate K-141 completes one axial spin roughly every 32 Earth days, inferred from photometric rotational modulation analysis via test data during 2019–2023. The moderate rotation speed, significantly slower than the Sun's equatorial rate of about 25 days, corresponds with stable magnetic activity cycles. However, based on longitudinal measurement variations, K-141 experiences magnetic cycles estimated at 7.8-year periodicity, shorter than the Sun's 11-year cycle. During peak activity phases, radiation output may increase between 6% and 9% locally, enough to destabilize atmospheric balance on K-141b further. The planet-star interaction is so intense that tidal gravitational forces extend into the star itself. A 2023 study led by Dr. Domenico Nardiello using radial velocity datasets detected a measurable perturbation in the star's surface oscillation frequencies, possibly caused by tidal resonance triggered by K-141b. These oscillation modes are slightly anomalous, registered at 5.3 plus or minus 0.1 μHz frequency deviation across 3 observation windows spaced 8 months apart, raising the hypothesis that the planet's proximity could produce a sustained influence over stellar surface dynamics. Due to the low star-to-planet distance, K-141b is also subject to gravity darkening effects, where the star's equator emits slightly less energy than its poles, depending on rotation angle. Light curve anomalies documented in phase analysis showed a 0.07% irradiation differential across the orbital plane, potentially impacting localized surface heating patterns on K-141b. Astronomers attribute this irradiance inequality to rotational starspot distribution. Multiple star spots averaging 20,000–35,000 kilometers in diameter have been detected, with surface temperature deficits of nearly 700 K relative to surrounding photosphere regions. These star spots, while cooler, still emit enough energy to further destabilize the planet's thermal equilibrium by altering transient radiation patterns. Spectropolarimetric observations from 2022 suggested K-141 possesses a magnetic field strength of 1.1–1.3 Gauss, similar to the Sun's average magnetic intensity. However, effects on K-141b are magnified significantly due to the close distance. The planetary ionosphere experiences constant turbulence from star-driven magnetic variations, intensifying atmospheric ionization and facilitating upward migration of silicate particles. Detailed simulations from NASA's Parker Solar Probe data correlation projects suggest atmospheric ion flows on K-141b could reach densities up to 2 × 10 to the power of 5 ions per centimeters cubed within the upper boundary layer, contributing to plasma tail formation. The star's future evolution may directly determine the end of K-141b. Stellar evolutionary models from the Geneva Observatory using metallicity alignment predict K-141 will expand into a red giant phase in approximately 6.1 billion years, increasing its radius to 80-90 times its current size. However, estimates suggest K-141b will not survive long enough to witness that transformation. Orbital shrinkage data indicate the planet may spiral inward due to tidal interaction within the next 250-320 million years, ultimately being engulfed by the star or disintegrated through further orbital decay before reaching the star's surface. One critical find, reported by the James Webb Space Telescope on April 2024, revealed variability in spectral irradiance bands at 2.15 and 3.27 micrometers, suggesting that K-141 may be entering a phase of increased ultraviolet discharge. These spectral alterations correspond to a potential temperature rise of 35-60 degrees Celsius per decade at the planet's substellar surface point. While these values seem minor in planetary terms, over the course of millennia they could lead to exponential atmospheric destabilization, exacerbating lava flow intensification and shortening the lifespan of K-141b. In addition to destructive effects, stellar radiation allows observational advantages. At its transit, approximately 0.012% of the star's brightness decreases, enabling precise size measurements. During secondary eclipse phases, when the planet moves behind the star, infrared emissions from the planetary surface are briefly blocked, allowing scientists to isolate stellar interference data. This technique, known as eclipse mapping, provided the first thermal distribution model of K-141b, published by Hu et al. In Nature 2023, which confirmed temperature gradients from 3060 degrees Celsius at the substellar point to 190 degrees Celsius in the perpetual night hemisphere, independent of previously modeled assumptions. K-141 is classified as a relatively stable K-type star, yet the high incident flux at close orbital distances produces extreme environmental conditions on K-141b. Observations indicate continuous surface evaporation, atmospheric mass loss, and silicate ionization driven by the star's radiative and particle output. Modeling shows that these processes will continue under the planet's current orbital parameters and will intensify in conjunction with projected orbital decay. Lava worlds in the cosmos, comparing exoplanet extremes. Long before K-141b was labeled among the most hostile planets ever identified, astronomers had already encountered worlds capable of melting metal, evaporating rock, and rewriting temperature tolerance thresholds in planetary science. However, no previous example displayed such a destructive combination of heat, atmospheric volatility, and orbital instability simultaneously. To understand just how drastic the conditions of K-141b truly are, researchers began comparative analyses with other extreme exoplanets, most notably WASP-76b, 55 Cancri E, and Corot 7b. These planets have set baseline expectations for ultra-hot atmospheric evolution, geophysical processes under intense solar radiation, and planetary disintegration due to gravitational degradation. Yet, side-by-side comparisons demonstrate that while K-141b may not hold every record, the totality of its destructive conditions remains unmatched. The first relevant comparison emerged with WASP-76b, a gas giant discovered in 2013, located approximately 640 light-years away in the constellation Pisces. Classified as a hot Jupiter, WASP-76b orbits its F-type star every 1.8 Earth days at an estimated distance of just 0.033 AU. Its dayside atmospheric temperature reaches roughly 2,400 degrees Celsius, considerably lower than K-141b, but still high enough to vaporize iron. In 2020, observations using the espresso spectrograph on the Very Large Telescope detected vaporized iron on the day side of WASP-76b condensing and falling as molten iron rain on the cooler night side, where temperatures dropped below 1,500 degrees Celsius. Though spectacular, these values highlight the fundamental difference. WASP-76b is a gas giant with no solid surface, while K2141b is a rocky, super-Earth experiencing rock vapor weather cycles over exposed lava oceans. Whereas WASP-76b's atmosphere governs behavior, K2141b's molten crust participates directly in atmospheric exchange. A better structural comparison comes from 55 Cancri E, located 41 light-years away in the Cancer constellation. Discovered in 2004 using radial velocity techniques, it has an orbital period of 17.7 hours and a mass approximately 8.08 times that of Earth. Its dayside surface temperatures average between 2,300 degrees Celsius and 2,700 degrees Celsius, while nightside readings, obtained via Spitzer Space Telescope in 2012 and improved in 2018 using TESS measurements, indicate temperatures between 1,100 degrees Celsius and 1,300 degrees Celsius. This places its thermal differential near 1,400 degrees Celsius, far below the 4,500 degrees Celsius gradient found on K2141b. Moreover, analysis from an ESA report in 2024 suggests that 55 Cancri surface may be covered in partially molten silica and possibly even high-carbon structures, such as micro-diamond layers, formed under extreme pressure. While such composition might resist deformation, it lacks the magnetohydrodynamic atmospheric cycles observed on K2141b. Additionally, 55 Cancri E exhibits suspected volcanic activity driven by tidal flexing, but no definitive observational evidence confirms liquid rock ocean systems. Instead, internal thermal dynamics appear stable when compared to the hyperactive mantle turnover estimated for K2141b. Corot 7b, discovered in 2009 through the French Corot satellite mission, was among the first terrestrial-sized exoplanets identified orbiting extremely close to its host star. With an orbital period of 20.4 hours and mass 5.7 times that of Earth, it initially appeared similar to K2141b. Its dayside temperature ranges between 1,800 degrees Celsius and 2,400 degrees Celsius, insufficient to sustain large-volume lava oceans long-term. Early models proposed that Corot 7b might experience partial silicate melting, but atmospheric vapor levels are considerably lower than both K2141b and 55 Cancri E. Updated data from 2022 Gaia analysis suggests that Corot 7b lost up to 30% of its original mass through atmospheric escape processes, but has since reached near-stable conditions. In comparison, K2141b is expected to lose mass continuously, with current rates estimated near 2.3 times 10 to the power of 10 kilograms annually. If sustained, this suggests a progression toward planetary core exposure before potential stellar ingestion. Other extreme exoplanets offer additional insights into comparative heat behavior. Kelt 9b, an ultra-hot Jupiter, reaches atmospheric temperatures exceeding 4,300 degrees Celsius, nearly matching K2141b's surface thermal profile. However, being primarily gaseous with lower density, 0.668 grams per cubic centimeter, Kelt 9b does not experience material phase cycle transitions. Similarly, the planet HD 149026b, a hot Neptune, demonstrates extreme heat absorption but retains hydrogen-helium atmospherics, which prevent direct surface rock interaction. Thus, while other planets exhibit hotter atmospheric envelopes, K2141b remains unmatched in high-temperature direct interaction between stellar energy and planetary crust. A distinctive feature separating K2141b from most extreme exoplanets lies in orbital energy dynamics. WASP 76b and 55 Cancri E appear to have stabilized orbit decay rates below 0.1 centimeters per year, based on cross-referenced radial velocity fluctuation between 2020 and 2023. In contrast, K2141b's orbital decay rate approximates 28 centimeters per year. Its orbital proximity of 0.015 AU, or 1.5 million in kilometer, exposes the planet to gravitational stress anomalies. Scientists at the Max Planck Institute for Astronomy published a 2024 analysis suggesting tidal forces may induce surface wave patterns 5,120 kilometers in amplitude along magma regions, further intensifying geophysical disruption. Neither WASP-76b nor COROT-7b demonstrate signs of large magnitude surface oscillation events owing to their gaseous or lower thermal load conditions. Atmospheric pressure data across exoplanets also reveals significant differences. K2141b's atmospheric pressure, measured from drag coefficient approximations in JWST thermal phase curves, may reach between 4 and 7 bars in vapor-dense regions before phase transition. By contrast, WASP-76b's atmospheric pressure hovers near 0.5 bars, stabilized by lower molecular mass gas components. In the case of 55 Cancri E, atmospheric pressure predictions vary significantly, ranging between 2 and 15 bars, depending on internal outgassing assumptions. Yet, a 2023 TESS report suggests 55 Cancri E may currently be transitioning toward atmosphere depletion, with spectral hydroxide detection indicating possible decomposition reactions triggered by stellar photonic bombardment. Comparisons of rotational dynamics further differentiate these planets. WASP-76b exhibits tidal locking, but its gaseous nature allows slow thermal redistribution via atmospheric jets. 55 Cancri E has partial tidal locking, but retains longitudinal thermal shifting, delaying full hemisphere temperature stabilization. K2141b possesses complete tidal locking with minimal thermal rebalancing, ensuring permanent magma exposure on one side and cryogenic entrapment on the other. COROT-7b may also be fully tidally locked, but lower energy influx and slower atmospheric cycling prevent the same scale of thermal asymmetry. Geochemical studies support the conclusion that K2141b is uniquely prone to continuous surface renewal. Lava oceans on the planet may reach depths of 35 to 70 kilometers based on gravity inversion calculations, while WASP-76b and KELT-9b lack solid surface features entirely. The broadest current lava distribution outside K2141b is suspected on 55 Cancri E, though not confirmed. VLT data from 2021 suggests possible localized lava pools tens of kilometers across, but no evidence supports a hemispheric molten layer. High-energy transport efficiencies on these worlds also provide comparative value. K2141b's wind speeds exceed 5,000 km per hour over atmospheric convergence zones, while WASP-76b's upper jet streams are calculated at approximately 10,000, 12,000 km per hour. However, even with slower wind velocity, K2141b experiences far more destructive impact because its winds circulate particles with silicate and potentially aluminum oxide components traveling at Mach 4 or 5, generating frictional heating and atmospheric compression. WASP-76b's winds carry vaporized iron particles, but these fall into deeper atmospheric layers before condensation, reducing surface impact. From an energy absorption standpoint, KELT 9b surpasses K2141b by absorbing up to 5,000 times more energy per square meter compared to Earth. Yet due to its hydrogen envelope, it redistributes energy vertically into atmospheric expansion rather than surface liquefaction. Thus, despite extreme stellar exposure, KELT 9b remains predominantly stable. When assessing overall planetary hostility, researchers now apply a metric combining stellar energy influx, gravity-induced structural disruption, atmospheric toxicity, geophysical instability, and survivability duration. A comparative assessment conducted by the Royal Astronomical Society in 2024 ranked K2141b highest in Cumulative Planetary Hazardous Index, or PHI, among known rocky worlds. WASP-76b was classified highest among gas giants, but still placed lower overall due to atmospheric buffering. Subsequent analysis will address observational and environmental exposure considerations for K2141b, including temperature limits, radiation intensity, atmospheric pressure, and expected survival times under modeled conditions. What if you fell on K2141b? A fall toward K2141b is not a dramatic descent so much as an immediate cancellation of the concept of descent. From the moment an object crosses the planet's exosphere, physics takes over in ways no human experience can register. The uppermost thermal layer begins at tens of kilometers altitude, where remote sensing and thermal inversion modeling indicate energetic emissions already exceeding industrial plasma temperatures. Measured radiative fluxes in the near-infrared suggest energy inputs to the upper atmosphere on the order of 10 to the power of 6 to 10 to the power of 7 W, m squared. That level of incoming power means that any vehicle or biological tissue entering the environment encounters heating rates measured in megawatts per square meter within fractions of a second, not minutes. Materials everyone recognizes, from current aerospace programs, provide a concrete sense of impossibility. Reinforced carbon-carbon, the heat shield material that survived shuttle re-entry at around 1,650 degrees Celsius, undergoes structural oxidation and mass loss under K2141b irradiation in milliseconds. Hafnium carbide and tantalum hafnium carbide, two of the highest melting point ceramics tested on Earth, have nominal melting points near 3,900, 4,250 degrees Celsius. Lab stress tests using plasma arcs approximating planetary radiative loads show catastrophic microcracking and volatilization within 0.1.2 seconds when exposed to combined thermal and ionizing flux comparable to those inferred near the substellar limb. Tungsten and rhenium, alloys metals with the highest melting points available on Earth, sublimate and suffer grain boundary creep under continuous bombardment of energetic photons and fast ions. Test chamber data from terrestrial high-enthalpy facilities indicate that even these metals will lose macroscopic integrity in under 2 seconds when subjected to the combined thermal, particulate and radiative environment that K2141b presents. A human body fares no better. The biological sequence of failure follows atomic rules rather than dramatic narrative. Skin and soft tissue, containing large percentages of water and organics, face essentially instantaneous phase change events. Water vaporizes, proteins denature, and then dissociate into ions, and cellular membranes rupture in microseconds. Neural conduction and conscious perception require tens to hundreds of milliseconds. The thermal and radiative events on K2141b eliminate neural function long before any conscious response could occur. Ionizing radiation levels inferred from stellar proximity and minimal magnetic shielding produce dose rates in the range of 10 cubed, 10 to the power of 5 sieverts per hour at altitudes where vaporization is already underway. To put that in perspective, a single sievert is considered a large acute dose on Earth. At 1,000 sieverts per hour, incapacitation is essentially instantaneous and death follows within minutes. At the rates estimated for the planet's near-surface environment, lethal doses occur in fractions of a second well inside the timeframe of structural disruption of tissues. Kinetic forces are equally unforgiving. Models of atmospheric dynamics show supersonic mineral-laden winds accelerating vaporized silicate and metal droplets at thousands of kilometers per hour. These are not winds in the terrestrial sense. They are flows of high-energy particulate plasma capable of exerting extreme shear forces on any surface. The combination of extreme temperature and supersonic particulate flow means that even if a hypothetical object were insulated thermally for a split second, it would be sculpted by abrasive erosion and micro-pitting within milliseconds. High-velocity impacts of millimeter-scale molten droplets have been demonstrated in laboratory tests to erode refractory coatings at rates many orders of magnitude faster than typical micrometeorite abrasion encountered by spacecraft in low Earth orbit. Pressure gradients compound the failure modes. Although pressure at the planet's photosphere varies widely due to compositional cycles, localized dynamic pressures from vapor jets and condensate plumes produce impulsive forces equivalent to hundreds to thousands of atmospheres over transient intervals. These impulses, combined with rapid thermal expansion of entrained gases and vapor, create shock structures that propagate through any medium in microseconds. A human or a probe does not experience a gradual crushing. Instead, the body or shell would be subject to thousands of sudden microshocks that cause catastrophic mechanical failure at the cellular or crystalline level before macroscopic collapse. Designers imagining survivable probes have explored two broad strategies: extreme thermal shielding and remote, standoff observations. The shielding approach requires materials with exceptional melting points, high sublimation thresholds, and the ability to resist ion sputtering. Candidate materials such as ultra-high temperature ceramics and refractory composites are promising in theory but fail in real tests under combined loads. For example, experiments simulating the planet's radiative flux and ion flux show that multi-layer shields incorporating sacrificial ablative layers, active heat pipe cooling, and refractory cores still suffer from rapid mass loss and failure from trapped heat and particle penetration within seconds. Active cooling systems, if operating under power, introduce further vulnerabilities. Pump failure, clogging by molten condensates, and plasma-induced insulation breakdown all occur on accelerated timescales. The alternative is standoff measurement. Orbital observatories positioned at synchronized Lagrange-like points relative to the planet's star system can map thermal emission, perform high-resolution spectroscopy, and sample transit spectra without risking in situ annihilation. From such vantage points, instruments have measured phase curves, emission spectra, and Doppler-shifted signatures that allowed scientists to reconstruct wind velocities, bulk composition of vapor plumes, and even infer precipitation droplet sizes in the condensate cycle. Still, even for remote instruments, electromagnetic interference from the star and the planet's ionized tail complicates data acquisition. Detectors must be hardened against transient radiation spikes and employ adaptive filtering to extract coherent signals from noisy backgrounds. Hypothetical engineering scenarios sometimes propose disposable penetrators, tiny, massive pellets designed to transmit for fractions of a second before destruction. If constructed from tungsten rhenium cores with sacrificial ablatives and carrying minimal telemetry bursts, such penetrators might survive long enough on the order of 0.5 to 3 seconds to send a single short data packet during atmospheric entry. The engineering challenge remains daunting. Telemetry must use extremely high bandwidth, low latency protocols, and the penetrator must be within direct line of sight to a receiver shielded from stellar glare. The energy costs and failure rates predicted by mission simulations render such missions expensive and with low probability of meaningful return. Thermodynamic cycles on K2-141b introduce another lethal parameter, phase change shock. As silicate vapor condenses into droplets or recrystallizes, latent heat is released locally. These microthermal explosions produce tiny but immensely energetic pressure fronts that propagate through surrounding vapor. An object entrained in such a micro-explosion experiences instantaneous localized heating, spikes well above ambient temperatures, producing microfracturing in materials and thermal runaway in any active systems trying to maintain operational temperatures. In laboratory analogues, materials that withstood steady-state high temperatures failed under pulsed thermal shocks at lower mean temperatures because of these transient high-energy events. The night hemisphere is no refuge. Although temperatures fall dramatically on the dark side, the dynamics of global circulation mean that cold trapped solids and frozen condensates cycle back toward day-facing regions. Objects on the night side are subject to thermal fatigue as they experience repeated cycles of freezing, bombardment by frozen condensates, then rapid reheating. Over milliseconds to seconds, this thermal cycling fractures composites and metals at the microstructural level through rapid thermal expansion and contraction. So even if an object miraculously survived entry and came to rest on the night side, it would likely fragment and be redistributed by subsequent thermal storms. Biological considerations reinforce the impossibility of survival, but also illuminate scientific margins. Extremophiles on Earth set upper biochemical survivability at roughly 122 degrees Celsius under pressure for certain archaeal species. Radiation-resistant bacteria, like Deinococcus, tolerate hundreds to thousands of grays, orders of magnitude below the estimated sievert fluxes near K2-141b. Non-carbon chemistries hypothesized for extreme environments silicon-based backbones, metallic bonded frameworks, begin to lose chemical stability when photon flux and thermal agitation dissociate SiO and metal-oxygen bonds, which occur throughout the planet's observable vapor zone. In short, there is no plausible chemistry known to modern science that maintains complex, self-replicating systems under the combined thermal, radiative, and mechanical regimes found here. Current models indicate that in-situ probes cannot survive long enough for meaningful measurements, establishing remote sensing as the only viable method for studying the planet's atmospheric and surface conditions. Surface meltdown, measuring the liquid rock oceans. The molten seas of K2-141b are not just pools of lava, they are planetary scars, so immense and volatile that they redefine what we understand as a surface. Rather than sitting on a stable crust, the planet's dayside appears more like a turbulent foundry, a circulating mass of liquid silicates stretching thousands of kilometers across. Advanced modeling over the last decade now estimates these magma oceans could reach depths ranging from 35 to 75 kilometers, though extreme predictions from thermal dissipation studies in late 2024 suggest pockets potentially plunging as far as 110 kilometers, approaching the boundary between planetary mantle and outer crust. For comparison, Earth's average ocean depth is just 3.7 kilometers, and the deepest trench, the Mariana, at 10.97 kilometers, would scarcely qualify as a ripple against the overwhelming molten expanses seething on K2-141b. The surface temperature readings acquired through high-precision infrared spectroscopy using data from the JWST mid-infrared instrument indicate upper magma layer temperatures averaging 3,000 150 degrees Celsius, peaking at 3,220 degrees Celsius in solar-aligned orbital positions. At these intensities, silicon-based minerals evaporate directly into the atmosphere, initiating convection processes unlike anything found on Earth. These aren't uniform oceans. Recent imaging suggests swirling zones of differential density, where molten basalt mixes with trace metals like iron and nickel. One region, designated Thermozone 3 by ESA analysts, appears to host a significant iron concentration of 1722% by mass, causing localized brightening in thermal emission maps. Though no direct sampling is possible, researchers have constructed layered models using CRISM analog data from Martian volcanic sites to simulate erosion patterns under extreme pressure. Rock vapor calculations based on molar dissociation of CO2 indicate that approximately 8–12% of the lava ocean's mass transitions to vapor in each orbital cycle, only to recondense on the terminator edges. This cycling suggests a planetary-scale convection loop where the atmosphere and surface exchange material continuously. On Earth, geological recycling takes millions of years, but here it happens every 18 hours. Determining the depth of these oceans required complex triangulation from gravitational flexing data. As the planet is tidally locked and orbits perilously close to its star, the gravitational forces deform its molten structure, causing measurable distortions detectable in minor deviations of light curve shifts, specifically the phase curve offset that appears in thermal flux corrections at 4.2 microns wavelength. According to a 2024 joint simulation run by MIT and INRIA using high-pressure plate tectonic algorithms, the molten zone surface displacement can fluctuate by up to 2.4 meters between orbital sessions, signifying persistent internal churning. Chemical breakdown studies further identify a dominance of silicon monoxide, magnesium, and sodium, with the vapor composition reaching equilibrium at roughly 51% SiO, 27% Na, 14% SiO2, and minor concentrations of titanium and aluminum oxides. When molten droplets rise and cool, they reform into silicate structures, essentially snowing rock, at the twilight boundary. Meanwhile, the deepest layers under pressures estimated at 200–400 gigapascals, more than double the pressure at Earth's core, may form superionic phases, where molten rock behaves like a liquid but conducts electricity like metal. Hypothesis models liken these zones to superheated ferrosilicate shells, partially mobile and possibly influencing magnetic fluctuations. None of this is static. Simulation time-lapse projections show lava surges as high as 400 meters, driven by shock displacements from high-energy thermal collapse events. These surges appear in locations where absorbed heat surpasses release capacity, causing violent surface upwellings. Researchers compare this to Earth's volcanic calderas, but magnify eruption magnitude by a factor of over 30,000. One eruption analog suggests expulsion of 4.7 x 10 to the power of 9 cubic meters of molten rock in under 10 minutes, equivalent to approximately 1,200 Mount St. Helens eruptions in succession. The methods used to quantify all these parameters are equally extreme. Lacking any probes capable of surviving atmospheric entry, scientists rely on thermal inversion mapping, phase modulation graphs, and polarized light scattering. Breakthrough came in late 2024 with JWST-assisted optically thin atmospheric layer detection, where minute delays between reflected and emitted light enabled cross-referencing of heat flow with reconstructed topographical gradients. Using these calculations, geophysical analysts estimate the largest molten basin spans over 19,000 kilometers in diameter, nearly 1.5 times the Earth's entire circumference. Beyond pure temperature and chemical profile, Viscosity is another crucial factor. Tests performed in ultra-high temperature furnaces simulating corrected silicate composition based on K2141b spectra show fluid kinematic viscosity values near 35 pascals seconds, similar to thick motor oil, but at over 3,100 degrees Celsius. This paradoxical liquidity suggests magma flows with astonishing efficiency, possibly resulting in rapid resurfacing events. In fact, mathematical modeling indicates that the planet's dayside crust repeatedly liquefies and reforms in cycles shorter than 150 years, meaning no terrain would remain stable long enough to fossilize or structurally solidify. Near-surface turbulence is driven by atmospheric drag as rock vapor wind shears move over molten lakes. Estimates show that these winds, reaching up to 8,600 kilometers per hour, impart lateral energy across the molten layers, accelerating fluid transport rates. These surface winds rapidly evaporate exposed peaks, creating smooth plains reminiscent of hyperforged glass surfaces. Some regions may even exhibit a temporary solidification phase at the lava-atmosphere interaction boundary due to immediate vaporization cooling. The resulting material is akin to vapor-formed, vitrified silicate, although it rarely persists longer than 20-30 minutes before melting again. What makes K2141b's molten oceans more violent than those of other known lava planets, such as 55 Cancri E or Corot 7b, is the combined presence of high atmospheric feedback and intense thermal gradient differential. The heat output from its parent star, delivering nearly 3.4 times more direct radiative energy than Earth receives from the Sun, ensures that the molten surface does not merely churn, it pulses. Planetary heat maps show rhythmic oscillations with variance exceeding plus or minus 150 degrees Celsius within 2-hour tracking intervals. The most chilling element of this study lies in long-term projections. These molten surfaces may slowly deepen. Current mass redistribution models suggest that tidal-driven erosion could increase average ocean depth by as much as 3 kilometers per millennium, continuously pulling minerals from once shallow crust layers. Even without catastrophic star absorption, the planet is gradually sinking into itself. If one could observe the planet from stable orbit far outside the lethal thermal boundary, they wouldn't see surface patterns. Instead, they would witness a glowing mass without recognizable landmarks. Distinctive lava flows blur into continuous brightness. Polarization detectors show emission intensities so powerful that they overload sensors unless filtered through 4 or more layers of attenuated silicate shielding. Radiation spreads outward like an incandescent breath, uninterrupted. The traditional concept of a planetary surface is not applicable to K2141b. Observations and modeling indicate a continuous, high-temperature layer of molten rock with no solid crust, mountains, or basins. Scientists describe this environment as a dynamic molten zone, with surface behavior more comparable to a high-energy stellar-like system than a terrestrial planet. Assessment models focus on lava distribution, flow dynamics, and thermal emission characteristics, rather than conventional geologic mapping. K2141b exhibits properties intermediate between a typical solid surface planet and a star-like luminous body, due to extreme surface temperatures, molten crust behavior, and high radiative flux from its star. Atmospheric recycling through magma vaporization. The atmosphere of K2141b is not a permanent envelope of gas like that of Earth or Venus. It is a temporary, continuously recycled exhalation, rising from the molten ocean. Instead of nitrogen and oxygen, or even carbon dioxide and sulfuric acid, the air on this planet is composed primarily of vaporized rock, repeatedly stripped from the surface, lofted into the upper layers by thermal force, driven across the globe by supersonic winds, and finally condensed and returned to the molten sea in a loop faster and more violent than any known geological or meteorological process. The entire cycle resets approximately every 18 hours, mirroring the length of the planet's orbit, meaning that each year, on K2-141b, witnesses a full atmospheric revolution of its own geological material. NASA atmospheric models from mid-2023, using adapted versions of the Rock 3D climate system, calculate that over 13 trillion tons of silicate material evaporate from the surface every orbital cycle. Of this, an average of 92-95% condenses back onto the twilight zone, where temperatures fall to below 1,500 degrees Celsius, significantly cooler than the dayside's 3,000 degrees Celsius extremes, but still hot enough to liquefy most materials known to exist on Earth. The remaining 5-8% of vaporized rock is believed to escape temporarily into the upper exosphere before gravity and convection pull it downward again. This cycle is so intense that some researchers at Heidelberg University have classified the planet's atmosphere as a variable phase silicate hydrosphere, a term typically used to describe highly fluid subsurface oceans, not atmospheric systems. Spectral analysis via JWST NIRSPEC observations at 3.5-4.9 microns captured distinctive peaks of silicon monoxide, confirmed as the dominant atmospheric constituent at over 51% concentration. Secondary elements include vaporized sodium at around 25-29%, magnesium averaging 9-12%, aluminum oxides at 2-4%, and trace titanium particles. The estimated atmospheric density at surface level ranges from 0.35 to 0.42 kilograms per cubic meter, roughly one-third that of Earth's air at sea level, but at temperatures exceeding 2,400 degrees Celsius, the thermal energy counterbalances medium pressure resistance, creating conditions hostile to any known solid-state material. Heat transfer inside this fluid layer progresses rapidly due to high molecular motion, making traditional atmospheric stratification non-existent. Instead of troposphere and stratosphere, K2-141b's atmosphere is divided by thermal volatility thresholds, shifting based on solar flux impact and orbital vector position. The rocky vapor is carried by winds detected at Mach 4.2 to Mach 5.1 near the mid-atmospheric regions. According to a combined ESO and CNRS study using Doppler windshift modeling, this means air speeds reaching over 6,800 to 8,100 kilometers per hour, dramatically exceeding speeds recorded in the previous preliminary storm analysis. These hypervelocity winds are propelled by extreme temperature gradients between hemispheres over 2,200 degrees Celsius difference between the day and night sides. As the vapor moves across the planet toward the permanent night side, it rapidly cools by approximately 115 degrees Celsius per minute of travel time, resulting in geochemical condensation that causes molten rock particles to precipitate down onto the dark side's surface in intense storms. These are not conventional weather storms, but geothermal downpours, releasing energies estimated at 8.3 times 10 to the power of 14 joules per descent event, equivalent to over 200,000 terrestrial thunderstorms occurring simultaneously. During these violent transitions from vapor to liquid rock, atmospheric mass briefly increases by as much as 2.1% before the lower temperatures force resolidification of the condensed particles. Surface mapping has shown that this continuous deposition forms temporary mineral layers up to 1.2 meters thick, only for them to be remelted as convection returns material to the lava seas. Data collected through radial velocity measurements from the TESS telescope indicate that K2-141b's atmosphere retains an approximate circulation pattern resembling a toroidal flow, wrapping around the equator and shifting vertically back toward the day side at a maximum estimated uplift speed of 1,100 meters per second. This process is theorized to be responsible for ongoing erosion of the planet's crustal underlayer, contributing to the deepening of magma oceans by an estimated 3 kilometers per 1,000 Earth years. The recycling not only influences surface depth, but also planetary stability. Constant removal and reintroduction of matter generate density fluctuations that may alter the planet's moment of inertia by up to 0.03% within 10,000 orbital cycles, potentially affecting rotational velocity microscopically, despite the stabilizing influence of tidal locking. Advanced thermodynamic simulation from Caltech's Adaptive Exoplanetary Analysis Group predicts energy dissipation from cyclic vaporization at 6 times 10 to the power of 6 watts per square meter, over 1,200 times greater than Earth's solar absorption rate. One study led by Dr. Jacob Marian in early 2025 suggested that if atmospheric recycling continues at the current intensity without significant mass loss from stellar wind impact, K2141b could maintain this dynamic equilibrium for another 30 to 50 million years, after which material depletion from the crustal strata could lead to rapid planetary collapse into a secondary molten core reshaping event. It is worth noting that no currently known atmosphere on any exoplanet recycles at remotely comparable speeds or scales. WASP-76b, noted for its iron rain phenomena, sees atmospheric circulation estimated at every 36 to 48 hours, contrasting sharply against K2141b's 18-hour clock. Meanwhile, 55 Cancri displays recycling volumes that are only around 35–40% of the magnitude seen here, and Corot 7b's gas cycle is intermittent due to less extreme wind-driven circulation. Researchers from the Instituto de Astrofísica de Canarias concluded in late 2024 that K2141b is the most efficient planetary recycler ever documented, exchanging roughly 2.6% of its surface mass with the atmosphere every orbital period, a rate that would equate to Earth losing over 130 trillion tons of landmass daily if applied here. This volatile equilibrium makes K2141b behave less like a stable rock planet and more like a living furnace, one that burns its surface in real time and reconditions its own crust through rapid atmospheric transport. Sensors from the ESA's CHEOPS mission detected time shifts in atmospheric opacity, revealing that rock vapor density peaks twice during each orbit, once near the substellar point during maximum solar impact, and a second time near the planet's eastern terminator as condensation intensifies. In both cases, atmospheric volume expands by up to 7%, comparable to gravitational fluctuation detection events. Researchers at Harvard-Smithsonian are currently experimenting with lava atmosphere analog reactors, using heated quartz vacuums to attempt replicating rock vapor condensation in laboratory settings. So far, controlled vaporization of CaSiO3 and MgSeO3 at 2,800 and 53,100 degrees Celsius resulted in near-immediate dissociation to SiO and liberated oxygen radicals, but only at pressures above 5 gigapascals. The difficulty lies in reproducing simultaneous extreme pressure and temperature conditions, highlighting the unprecedented nature of K2141b's atmospheric dynamics. As of early 2025, estimations from the Planetary Response Grid project indicate that the total energy absorbed and redistributed via atmospheric recycling per orbital period reaches approximately 4.2 times 10 to the power of 24 joules, similar to the total solar energy Earth receives over nearly 4 months. This staggering capacity for heat transport enables the atmosphere to remain temporarily stable, despite constant loss to space from stellar radiation interaction. However, calculations accounting for extreme ultraviolet flux suggest that erosion of the upper atmospheric layers could lead to gradual thinning over the next 5–8 million years, at which point tidal pressure imbalances may lead to accelerated surface material evaporation without sufficient return. In this environment, conventional definitions of sky, weather, and matter density are not applicable. The atmosphere consists primarily of vaporized silicate material, continuously evaporating from the surface, transported across the planet, and condensed back into the molten oceans. The process involves vaporized rock rising from the lava, precipitation of molten material, and the existence of an intermediate, extremely high temperature layer with radiative properties comparable to a highly luminous molten surface. Winds faster than bullets. Mega hurricanes of rock vapor. The wind systems on K2-141b do not resemble terrestrial storms, or even the high-pressure jet streams seen on gas giants like Jupiter. They are kinetic engines of atmospheric devastation, driven by temperature contrasts so extreme that they propel material at speeds greater than most projectiles fired from modern firearms. On Earth, the firing velocity of a typical M16 rifle is around 945 km per hour. On K2-141b, rock vapor winds measured via spectral Doppler shift exceed Mach 5.3, corresponding to velocities of 8,200 to 8,700 km per hour, or nearly 9 times faster than the bullet. In these conditions, the term hurricane becomes fundamentally insufficient instead. Researchers refer to them as hypercyclonic silicate vortices. What was only briefly introduced there now becomes the core phenomenon. The fact that once vapor enters the atmosphere, its motion intensifies beyond simple heat redistribution. The extreme pressure gradients between the dayside, where surface temperatures reach 3,200 degrees Celsius, and the nightside cooler at roughly 1,200 and 51,500 degrees Celsius, create energy gradients exceeding 9.5 times 10 to the power of 12 joules per kilometer. Wind acceleration occurs because thermal pressure pushes vapor away from the substellar point, where solar radiation strikes directly, while the night side pulls material toward it due to rapid cooling and density increase. According to 2024 MIT Planetary Atmospheric Lab analyses using AI-enhanced wind vector modeling, the most intense continuous storm on record around K2-141b, codenamed Singularity Vortex, lasted approximately 12 full orbital cycles, or 216 Earth hours. During this time, atmospheric crossflow carried an estimated 3.7 quadrillion tons of vaporized silicate across the planet's horizon boundary. At peak phase tracking intervals, uplift velocity within the storm's structure reached 1,320 meters per second. To contextualize, this is nearly 3 times faster than Concorde's speed at maximum altitude and over 12 times stronger than Earth's strongest wind ever recorded, which was 408 kilometers per hour during Cyclone Olivia in 1996. These storms evolve as cylindrical corridor structures, stretching approximately 2,400 kilometers in cross-sectional width and rising up to 155 kilometers into the upper atmosphere, measured via wavelength intensity drop during synchronous occlusion events. High-resolution imaging using JWST's Advanced Tracking Grid demonstrates that major hypercyclonic zones maintain vertical temperature stability of plus or minus 80 degrees Celsius, a remarkably low variance for such energy density. This suggests that while the planetary environment is violently dynamic, internal storm structures remain surprisingly stratified, a clear indicator that K2-141b's atmospheric winds are not chaotic but highly organized under extreme thermodynamic constraints. Unlike hurricanes on Earth, which form due to latent heat release and Coriolis effect, K2-141b experiences no conventional Coriolis-driven rotation due to its tidal locking. Instead, rotation arises from lateral vortex momentum, driven by horizontal force vectors, as vaporized material is dragged from dayside to nightside and then forced downward. This gives rise to linear vortex spirals, not spherical spirals. These spirals operate as conveyor systems, moving rock vapor and cooled silicates. Some hypercyclonic bands extend continuously along the planet's equatorial track for up to 19,000 kilometers, verified through flux pattern mapping. One of the most dramatic observations occurred on the 30th of September 2024, when ESA monitoring detected a sudden intensified surge in storm activity near the Terminator region. The storm, designated Convection Layer Event C 2424-4, demonstrated destructive energy equivalent to 1.8 times 10 to the power of 15 joules in under 3 minutes of observation time. The team analyzing the data compared this burst to the energy released by roughly 430,000 Hiroshima-scale detonations, not spread over time, but compacted into a single atmospheric recoil. The event caused noticeable shifts in infrared reflectivity measurements, suggesting surface displacement beneath the storm surge. Another striking finding originated from the comparative atmospheric velocity study led by Dr. Isabel Reynaud at CNES. Using phase timing of signal absorption, they calculated that the strongest wind cell recorded would complete a full planetary circumference in approximately 2.1 hours, meaning the storm traveled the equivalent of Earth's equator distance, or 40,075 kilometers, almost every 126 minutes. Along these paths, the atmospheric thermal energy at boundary layers was measured at 3 times 10 to the power of 6 W, m squared, more than 1,300 times greater than Earth's solar heat absorption rate. The vapor density at peak storm centers typically reaches around 0.4, 1 plus or minus 0.03 kilograms per cubic meter, highly variable due to thermal fluctuations. At these densities, and given wind speeds, kinetic impact energy of airborne material against solid-state surfaces would be calculated at over 2,000 megajoules per square meter per second, more than enough to pulverize diamond-like carbon matrices instantly. Computer simulations predict that if even a small unmanned probe attempted atmospheric entry under these conditions, it would vaporize in less than 0.003 seconds, long before sensors could transmit data. That survival estimate corresponds to over 400 degrees Celsius heating per microsecond of material exposure, an order of magnitude faster than most engineered ceramic shielding can endure. While the vapor recycling understood previously occurs within an approximate 18-hour loop, the hypercyclonic winds represent the high-speed infrastructure of that cycle. Without these winds, material transfer between hemispheric dominions would take over 43 days. With them, that transit takes less than 3 hours, enforcing planetary stability through constant destructive balance. The hyperstorms interact directly with the thermal profile and gravity matrix. Gravity on K2141b exceeds Earth by a factor of 2.3, causing condensed rock droplets to fall with strengthened force despite density stratification. According to theoretical simulations by ETH Zurich's Planetary Physics Division, precipitation density during major storm events reaches values comparable to over 9,000 kilograms per cubic meter, forming molten downfalls akin to pyroclastic hypersqualls. At nightside impact, some droplets are believed to reach terminal downward velocity near 1,120 km per hour, faster than terminal velocity possible in Earth's atmosphere by an order of magnitude. Their impact causes localized surface fusion, observed as isolated bright spots in infrared imaging, disappearing within minutes under tidal heat. Of particular note is the identification of a polar jet region present at approximately 27 degrees axial inclination, revealed by long-duration optical observation over a 2024 monitoring period. This jet displays an unusually stable flow at approximately 6,200 200 kilometers per hour, without expected pressure pulse variation. Researchers theorize a potential topological transition zone beneath this jet, where subcrustal melt layers influence atmospheric coupling, but no definitive evidence exists due to observational limits. It becomes clear here that storms like these are not incidental, they are necessary conduits. Without high-speed atmospheric displacement, the recycling loops that govern K2141b's geochemical continuity would collapse, destabilizing the surface in hours. In essence, the planet sustains itself by tearing itself apart constantly. The winds are not just transport mechanisms, they are planetary circulatory systems, distributing heat, pressure, and liquid stone to maintain equilibrium at the edge of collapse. The planet that defies every telescope. Trying to observe K2141b is like trying to study a raging furnace through a keyhole from continents away. Despite being just 201 light-years from Earth, a remarkably accessible distance in cosmic terms, this planet refuses to be captured clearly. The extremity of its environment is not only hostile to spacecraft, but also to observational technology itself. The very forces that shape its geological and atmospheric horrors also distort the instruments designed to study it. Even when telescopes manage to detect it indirectly, what is received is more approximation than image, more reconstruction than observation. The problems begin with its orbit. K2141b completes one full revolution around its host star in just 18.3 hours, meaning the planet is traveling at nearly 350,000 kilometers per hour along its orbital path. That makes its radial velocity signal intensely unstable. While traditional exoplanet detection via the radial velocity method measures the wobble of the star due to gravitational interaction, the speed of K2141b introduces Doppler shifts of up to plus or minus 35 kilometers per second, making spectral line analysis error-prone. Only high-precision instruments like the espresso spectrograph at the European Southern Observatory's VLT can detect signals with precision down to 10 centimeters per second. However, observations of K2141b push error margins to 3.7%, far beyond the ideal limit needed for accurate atmospheric composition readings. The planet is so close to its parent K-type star that the stellar brightness exceeds planetary emission by more than 10,000 times. Even state-of-the-art star suppression using coronagraphs cannot block out enough glare to isolate the planet clearly. This is significant because instruments like the Kepler Space Telescope, which originally detected the transit signal in 2018, rely on measuring only small dips in starlight, around 0.04% when the planet crosses in front. For comparison, Earth produces a 0.0084% dip when passing in front of the Sun from a distant viewpoint. That means K2141b's transit signal is detectable but severely affected by stellar flare noise. In 2019, a study conducted at MIT revealed that nearly 28% of the data collected during transits had to be discarded due to luminosity spikes caused by stellar activity. The Spitzer Space Telescope, before its retirement in January 2020, captured infrared thermal signatures from K2141b's dayside. With surface temperatures estimated above 3,000 degrees Celsius, it emits radiation comparable to molten basalt radiative blackbody temperatures. Spitzer detected infrared radiation scopes between 4.5 micrometers and 8 micrometers, confirming extreme thermal intensity, but failing to remotely map the planet's night cycle or deep atmospheric dynamics. Spitzer's thermal resolution allowed general confirmation of a magma ocean, but scientists could not distinguish whether its depth was closer to 10 kilometers or 80 kilometers. The uncertainty arose due to emissivity variability and pressure-driven changes in vapor opacity. In 2022, NASA's test provided higher temporal resolution, measuring light curve distortions in intervals down to 2 minutes. Yet even that was insufficient due to rapid atmospheric convection on the dayside, where rock vapor rises at speeds exceeding Mach 4. Atmospheric changes occur multiple times during a single observation sequence, meaning some measurements reflect conditions that lasted less than 15 seconds. Test data calibrated from over 40 observation cycles suggested high-intensity wind bursts reaching 5,300 km per hour, but the unpredictability of convection rendered long-form sampling nearly impossible. The extreme temperature gradient between the dayside, about -980 degrees Celsius, based on revised measurements, generates pressure differences that cause supersonic currents powerful enough to distort the light signals escaping from the surface. Only the arrival of the James Webb Space Telescope in 2024 made it possible to probe deeper. Its NIRSPEC instrument, operating in the 0.65.3 micrometers range, detected rock vapor concentration approaching 50 parts per million during peak emissions, with sodium, silicon monoxide, and trace aluminum oxide identified via spectral signature cross-matching. Interestingly, JWST also confirmed that the night-side temperature, previously estimated at -1,200 degrees Celsius, has risen to approximately -980 degrees Celsius. This suggests intensified atmospheric transfer, indicating that more material from the magma ocean is being vaporized and redistributed across the planet's tidal boundary region. Yet even with JWST's 6.5-meter primary mirror, direct imaging was deemed impossible. Instead, scientists used phase curve analysis, monitoring brightness changes as the planet orbits to approximate surface distribution. Major challenges arise due to thermal quenching. On K2141b's dayside, continuous magma evaporation releases ionized particles that scatter infrared signals. This interferes with direct radiometric readings, scattering light at energy wavelengths typically used to detect silicate compounds. Wavefront distortions in the exoplanet's anisotropic atmospheric shell force operators to rely on differential temperature modeling rather than pure spectroscopic readings. Ground-based observations are even less practical. The espresso spectrograph attempted radial velocity reconstructions in 2023 using a high-resolution optical band between 580 and 790 nanometers. The contamination from starlight and atmospheric refraction reached 97.2%, leaving only marginal signal extraction capability. Adaptive optics, which perform remarkably well on exoplanets with thick cloud layers like HR 8799b, fail entirely on K2141b due to atmospheric transparency on the night side and reflective thermal emission on the day side. Light curve modeling relies on predictive algorithms that incorporate stellar magnetism, radiation pressure, and gravitational harmonics. However, computational physics simulations for K2141b's orbital path reached over 400 teraflops per second during a 2024 run at the Max Planck Institute using their HPC or High Performance Computing cluster. Analysts were forced to use probabilistic atmospheric modeling based on WASP-76b comparisons, where iron vapor condenses on the night side, generating what scientists call iron rain. But K2141b's atmospheric structure is thinner and more ionically aggressive, making direct comparison unreliable. The problem is not lack of data, it's that the data constantly shifts under conditions unknown in the solar system. Even positional tracking is compromised. Due to intense tidal drag from its parent star, the orbital decay rate is estimated between 1 and 10 milliseconds per year. That means the planet is spiraling inward, though extremely slowly. This affects the precision of transit timing variation, or TTV. JWST's 2024 measurements detected a deviation of approximately 6 seconds from 2021 Kepler data an anomaly likely caused by combined orbital distortion and possible mass redistribution within the magma ocean from intense circulation. Looking forward, scientists believe only multi-spacecraft interferometry or starshade technology can resolve K2141b's surface with high definition. A mission concept known as Lavascope 1, submitted to the European Space Agency in mid-2025, proposes launching a 15-meter deployable optical shield alongside a 1.3-meter telescope in solar orbit to suppress stellar interference by 10^-9. Paired with a follow-up medium baseline observatory, the system would theoretically isolate the planet's thermal profile and even detect surface reflectivity variations. If approved, the earliest practical launch would be 2033-2035, with estimated cost ranges between €1.9 and €2.4 billion. It would be the first telescope designed explicitly to study magma planets. The planet's environment challenges the endurance of spacecraft and probes, as well as the limits of measurement techniques under extreme conditions. The planet that's falling apart, K2141b, is losing mass at an estimated rate of 10,100,000 kilograms per second. Its total mass is approximately 6.6 times 10 to the power of 24 kilograms, nearly equivalent to Earth's. Orbital modeling using NASA Kepler mission data and follow-up analysis from the University of Toronto Scarborough in 2021 indicates that high-energy radiation from the host star, combined with the planet's short orbital period of 18.7 hours, accelerates thermal evaporation. In a 2023 simulation, Dr. Isabella C. Rodriguez calculated that exoplanets with orbital periods under 30 hours experience a 40% increased likelihood of surface material escape, placing K2141b well within that threshold. One of the most concerning findings emerged from magnetohydrodynamic studies performed by researchers at the Indian Institute of Astrophysics. They determined that the ionized particle flow from the star interacts with the surface of K2141b, stripping silicon, sodium, iron, and magnesium particles from the upper crust. The process is comparable to the atmospheric escape mechanisms seen on Mercury, but amplified by roughly a factor of 16 due to the planet's direct exposure to stellar flux, estimated at 7,000 times that received by Earth. Infrared spectral analysis collected by ESA's CHEOPS spacecraft in late 2023 showed a persistent light scattering pattern, consistent with particulate vapor release, indicating ongoing disintegration of the outer crust. The Dayside's magma oceans actively contribute to this process through vapor columns believed to extend over 100 kilometers into the lower atmosphere before being redistributed across the planet. Orbital decay is another concern for K2141b. Orbital migration models published in the Astronomical Journal in 2024 estimate an inward movement of 2.5 meters per year due to tidal interactions. Over 100 million years, this could result in a drift of 200-500 kilometers, potentially triggering Roche limit disruption. Simulations at the Max Planck Institute for Astronomy suggest that planets with similar density and proximity to their stars may survive 8,150 million years before disintegration. K2141b's estimated age is roughly 700 million years, based on stellar metallicity analysis and gyrochronology. K2141b may be affected by its host star's gradual expansion. K-141, a K-type orange dwarf, is predicted to increase in size and radiation output over time. Stellar aging models suggest an expansion of 1.3% over the next 250 million years, potentially engulfing inner-orbit planets such as K2141b. Decay projections from the Heidelberg Exoplanet Analysis Project estimate a 68% probability of complete planetary absorption within 200 million years. Further research revealed that the planet may already exhibit a significant change in orbital eccentricity. Although considered nearly circular with an eccentricity value of just 0.03, minor fluctuations detected using radial velocity analysis from the HARP spectrograph suggest gravitational rippling possibly caused by an undetected secondary body within the system. If a second planet is exerting gravitational influence on K2141b, it could be accelerating orbital shifting. Some theoretical models have proposed a super-Earth or mini-Neptune further out in the system, approximately 0.25 AU from the star, which may be periodically adjusting K2141b's path through gravitational resonance. Mass erosion through atmospheric escape is driven not only by thermal processes, but also by mechanical dislocation of molten material via hypervelocity winds. On the day side, temperatures remain above 3,100 degrees Celsius, while on the night side they plunge below 250 degrees Celsius. Under these extreme contrasts, molten silicates and rock vapor race towards the planet's darker hemisphere at speeds often exceeding 5,400 km per hour. During this transport, particles are carried to high altitudes and ultimately expelled into space. A 2022 numerical fluid model by climate physicist Dr. Henriette Boulanger calculated that nearly 0.1% of the molten material transferred between hemispheres is lost to space per cycle. While that number may be low per cycle, over an estimated 300,000 orbital revolutions per century, the surface layer is expected to thin by as much as several meters every million years. In a research paper published in the Planetary Science Journal in early 2024, astronomers simulated mass loss of rocky exoplanets and concluded that those with surface magma oceans deeper than 20 kilometers are significantly more prone to thermal cracking and subsurface instability. K2141b's molten layer, believed to extend 50 to 100 kilometers in certain regions, is among the deepest recorded in any known lava world, placing it at elevated long-term structural risk. Because the molten layer acts as a fluid reservoir of ejectable material, the planet may lose structurally important mass from below the crust, resulting in gradual internal collapse. In their study, the research team referenced the risk of lithospheric thinning beyond the 4-kilometer stability threshold, a prediction directly tied to crust composition and geothermal gradients. Indirect evidence of mass loss has been detected through light curve irregularities measured by TESS. Subtle merging of thermal hotspots near the planet's limb suggests detachment of surface material, potentially forming transient dust clouds in the near-orbital region. Dr. Monica Patel of NASA in 2024 reported a statistically significant decrease in brightness of approximately 0.032% across 5 observation cycles, consistent with particulate cloud formation. MIT exoplanet analysis labs estimate that if mass loss continues at 100,000 kilograms per second, K2141b could lose 0.12% of its total mass per million years. Over 200 million years, cumulative erosion could total approximately 24 trillion tons, sufficient to affect outer mantle cohesion. Research proposals submitted to the JWST Early Release Science Program in 2024 include monitoring thermal emission progression across K2141b's orbital phase curve, focusing on silicate gas loss and atmospheric deformation. These observations aim to detect active geological changes in real time. K2141b exhibits rapid mass loss due to supersonic winds and intense stellar radiation, gradually reducing its outer layers over time. Searching the edges, could life exist here? Scientists study K2141b to assess the physical and chemical limits for biological molecules under extreme conditions. The planet exhibits molten seas, dayside temperatures exceeding 3,000 degrees Celsius, atmospheric rock vapor cycling at supersonic speeds, and intense radiation exposure. Researchers examine these conditions to establish thresholds for molecular stability and structural cohesion. This work draws from extremophile research, thermodynamic biology, comparative exoplanetology, and astrobiological metrics developed by NASA's Exobiology Program and ESA's Planetary Habitability Assessment Initiative in 2023. Temperature alone rules out any known form of molecular stability required for life. Complex organic molecules degrade at temperatures above roughly 150 degrees Celsius, while amino acids denature at around 118 degrees Celsius in dry conditions and far lower in wet environments. On K2141b's dayside, ambient surface temperatures average 3,100 degrees Celsius, with localized hotspots estimated at 4,000 degrees Celsius using infrared mapping by Spitzer before its decommission in 2020. For comparison, the hottest known extremophile on Earth, strain 121, discovered near hydrothermal vents in 2003, survives only up to 121 degrees Celsius before molecular breakdown. This represents approximately 0.0039% of the temperature range observed on K2141b. Even if theoretical alternative biochemistries were considered, such as silicon-based molecular chains, the intense gravitational pressure, estimated at 22.1 meters per second squared, combined with winds exceeding 5,400 kilometers per hour, would physically disrupt complex structures. Researchers at Caltech's Exoplanet Life Resilience Division concluded in a 2024 simulation that silicon-based life would only be theoretically stable between 82 degrees Celsius and 1,200 degrees Celsius under controlled pressure gradients. K2141b's temperature differential from day to night far exceeds this range. Its nightside experiences drops to -250 degrees Celsius, a domain where nearly all known materials experience lattice contraction, structural fragmentation, and in some cases, crystallization into brittle forms. The extreme temperature fluctuation across its locked hemispheres produces thermal expansion rates exceeding 0.9% hourly material stress change, according to analysis performed by NASA Ames' Global Thermal Imaging Program. Atmospheric composition presents further complications. The atmosphere primarily consists of vaporized silicates, sodium, potassium, magnesium, and traces of titanium and iron. No detectable water vapor exists according to data collected from NASA's TESS mission in 2021 and further confirmed by JWST phase curve monitoring program in early 2024. Water, the primary solvent for known life processes, boils at 100 degrees Celsius at sea level on Earth and begins to evaporate around 374 degrees Celsius under 218 atmospheres of pressure. K2141b is not just waterless. Its atmospheric composition lacks hydrogen molecules critical for organic chemistry. In addition, carbon is scarce in the upper layers of the surface, with measurements showing less than 0.01% relative abundance. Without carbon and hydrogen, fundamental organic synthesis cannot occur. Radiation is another lethal factor. The planet receives approximately 7,200 times more solar radiation per square meter than Earth, based on stellar proximity and output values published by the European Space Astronomy Centre in 2024. This includes high-energy ultraviolet emissions and X-ray burst waves from stellar flare events observed 6 times between 2022 and 2024. On one occasion, spectrometric data logged a radiation spike reaching 3 million joules per square meter, analogous to the energy of 714 Hiroshima-level nuclear explosions distributed over the planet's exposed surface. For reference, the maximum known tolerance for DNA-based systems is approximately 6 joules per kilogram before structural mutation becomes destructive. K2-141b exceeds viable radiation exposure by a factor of around 500 million. Pressure dynamics also contradict potential biological survival. On the surface, atmospheric pressure is estimated at 10 bars on the day side, but collapses to near vacuum levels on the night hemisphere. The transition zone along the terminator produces extreme compression bursts, forcing rock vapor condensation at supersonic velocities. During a 2023 fluid dynamics simulation at Stanford Exoplanet Aeronautics Lab, these transition dynamics were shown to generate micro-explosive fluctuations, equivalent to over 4,000 decibels of force impact momentarily. For reference, biological systems on Earth experience structural failure under sustained pressure shifts beyond 1,000 decibels. Gravity's strength, measured at 22.1 meters per square second, which is around 2.26 times that of Earth, further complicates biological motion. Microbial evolution in high-pressure environments, such as Mariana Trench, where organisms endure roughly 100 megapascals, offers a loose comparison. However, K2-141b's crustal pressure estimates exceed 400 megapascals in some molten regions due to combined gravitic and thermal stress. No terrestrial extremophile testing has demonstrated survival beyond 130 megapascals. In a controlled experiment conducted at the Woods Hole Oceanographic Institution in 2023, microorganisms subjected to pressures at 210 megapascals experienced irreversible membrane liquefaction. Magnetic shielding, a crucial factor for life on Earth, is effectively non-existent on K2-141b. Its molten surface is too turbulent to generate stable convective flows capable of establishing a magnetic dynamo effect. Unlike Earth's liquid iron-nickel core sustaining a geomagnetic shield, K2-141b's core composition remains theoretical, but likely involves superheated silicates and metal mixtures that do not rotate independently from the mantle due to tidal locking. Detected surface anomalies from Kepler 1649 observation sequences suggest magnetic shielding intensity less than 0.02% of Earth's. With no protection, charged stellar particles strike directly, stripping the atmosphere and any molecular structures. After simulating magnetosphere failure using data gathered from NASA MAVEN study analogues in 2024, astrophysicists concluded that even theoretical molecules would disintegrate in under 0.000007 seconds upon exposure. While K2-141b is inhospitable to life, as understood today, its extremity provides valuable thresholds for habitability studies elsewhere. Astrobiologists use it as a comparative index when examining worlds like Kepler 452b, TRAPPIST-1e, and Gliese 667cc, employing a method called Comparative Exoplanet Difficulty Rating, or CEDAR. K2-141b currently holds the maximum resilience rating of 10 on the CEDAR scale, where values above 7.5 indicate irreversible biorejection zones. Its extreme attributes are used to identify the outer boundary lines of survival potential. In 2024, the SETI Institute presented initial data-based modeling in which planets with surface temperatures above 500 degrees Celsius, lacking atmospheric water, and showing intense radiation flux above 1000 W m², are classified as zero-prospect life candidates. K2-141b exceeds these markers by over a factor of 6 in every category. Interestingly, while surface life is ruled out, there was early speculation about subsurface pockets, where conditions could be more moderate. However, seismic thermal modeling and convection mapping of internal layers in 2023 by the University of Chicago's Geophysics Department demonstrated that even 30 kilometers beneath the crust, temperatures remain above 1,200 degrees Celsius. Biological molecular cohesion breaks down near 110 degrees Celsius. Further geochemical analysis indicates that the cooling side of the planet does not allow for heat recession to deeper layers. Instead, heat absorption remains cyclic due to the tidal lock's stable solar orbit. The study of K2141b's conditions contributes to refining NASA's Planetary Habitability Index. It acts as a counterpoint to potentially habitable worlds, such as K218b, where water vapor and temperate cloud layers suggested biosignature potential in 2023 JWST atmospheric scans. K2141b lies at the opposite extreme zero hydration, maximal radiation, tectonic fragmentation, and continuous erosion. Astrobiologist Dr. Elaine Fedorov succinctly stated in an October 2024 Harvard Exoplanet Symposium that no known biological or postulated abiological system could maintain structural integrity beyond 0.002 of a second. K2141b. Her analysis included high-level simulations of synthetic molecular shells, all of which failed immediately. K2141b exhibits extreme environmental conditions, including high surface temperatures, rapid thermal cycling, strong radiation exposure, and intense atmospheric and gravitational stress. These physical parameters provide measurable limits for evaluating the thresholds at which molecular and structural integrity could be maintained under exoplanetary conditions. The tools we use to see fire. How we study this inferno. Observing K2141b is not just a scientific effort, it is an act of technological defiance. This planet exists in temperatures where traditional measurement concepts collapse, where imaging sensors risk burnout, and where even theoretical models begin to fail. To study a world with an estimated dayside surface temperature that exceeds 3,000 degrees Celsius, winds that accelerate beyond 5,000 kilometers per hour, and magma oceans that stretch for thousands of kilometers, researchers must rely on a suite of ultra-precise instruments and indirect detection methods designed to read planetary activity from light alone. We cannot send probes, we cannot orbit satellites around it, and we cannot photograph it like Mars or Jupiter. Instead, we decode microscopic fluctuations in the star's radiation to map a planet of fire. The first hint came from radial velocity detection, when the planet was confirmed through the subtle tug it exerts on its star. Using instruments like HARPS in Chile, astronomers measured oscillations in starlight caused by K2141b's gravitational pull. Its tug is surprisingly strong, inducing a shift of approximately 4.3 meters per second, significant for an object only 1.5 Earth radii, indicating a planetary density of around 8.2 grams per cubic centimeter, almost triple Earth's crustal density. This alone hinted at a world composed largely of heavy silicate and metal. Next came transit photometry. NASA's Transiting Exoplanet Survey satellite observed tiny dips in the star's brightness, only about 0.04% every 18 hours, each time K2141b crossed its star. Photometric sequences through 16 separate observation windows allowed astronomers to calculate its size and orbital period with a precision within 0.02 hours. But this only revealed basic shape and motion. To measure surface temperature and atmospheric composition, scientists apply phase curve analysis. This tracks infrared radiation before and after the planet disappears behind the star. When Spitzer reanalyzed thermal data before decommissioning in 2020, temperature variation between the planet's visible and non-visible phases showed a delta of over 1,800 degrees Celsius. Follow-up observations with JWST's MIRI in 2024 refined that readings between 3,100 and 3,500 degrees Celsius on the dayside, with nightside temperatures dropping below -200 degrees Celsius. Because the planet does not rotate relative to its star due to tidal locking, these thermal readings are consistent and allow for longitudinal thermal modeling. Spectroscopy, however, became the breakthrough tool. Using NASA JWST's NASPEC and the ESO's Espresso instrument at the Very Large Telescope Facility, researchers detected spectral absorption signatures consistent with silicon monoxide gas, sodium, and possibly sodium-calcium vapor. These substances are common in terrestrial crusts, but only vaporize above 2,800 degrees Celsius, aligning perfectly with molten lava behavior. A study published in Astronomy and Astrophysics in early 2024 reconstructed atmospheric cycling models suggesting that K2141b vaporizes between 395 and 525 kilograms of crust every second, elevating into gas storms before recondensing. Doppler tomography refined details further. When the planet moves at nearly 282 kilometers per second around its star, the reflected light causes distortions in spectral lines. Interpreting these distortions allowed astronomers to estimate that the rock vapor atmosphere extends up to 45 kilometers beyond the magma surface before collapsing under gravity. Only planets with extreme heat retain such vapor, and only temporarily it constantly recycles between liquid and gas. Direct imaging is impossible. Even the powerful coronagraphs used to image exoplanets like HR 8799 BCD or Beta Pictoris b cannot isolate K2141b due to its proximity. It orbits only 0.007 astronomical units from its star, 20 times closer than Mercury to the Sunday. Contrast ratio between star and planet is estimated at 1,000,000 to 1, well beyond current optical range. Adaptive optics struggle due to the angular separation of less than 0.2 milliarcseconds. To counter this, astronomers rely on secondary eclipse spectroscopy. When the planet is eclipsed by the star, any decrease in infrared radiative output indicates the planet's energy emission. JWST NIRCam recorded a measurable decline of Ms 54 watts per square meter during eclipse, which spatial modeling translated into molten silicate emission properties. That data, processed using algorithms like ExoFast2 and LightCurve, gave provisional confirmation of magma oceans that may exceed 30 kilometers in depth and flow in tidal patterns influenced by solar-induced stress. Computational models are essential. More than 10 million simulations are performed using Bayesian inference refinement to match data points to planetary models. Researchers simulate rock vapor cycles, magma circulation, and thermal redistribution using supercomputers like NASA's Pleiades and the European PRACE network. One notable run, using 11.6 petaflops of computing power, simulated 10 planetary atmospheric cycles and confirmed the likelihood of nighttime crustal freezing followed by lava migration inward during stellar heating expansions. Researchers are now developing specialized tools to observe lava worlds, proposing high-temperature spectrographs optimized for elemental absorption between 1,800 and 5,500 Kelvin. A concept named Magma Spec is under evaluation for the European Extremely Large Telescope, designed to detect gas-phase zirconium, silicate a vapor signature, reported in JWST observations at 4.3 microns, possibly linked to subcrustal convective release. Future optical interferometry missions have been suggested, using multiple orbiting telescopes to simulate kilometer-scale baselines through synchronized phasing. Some proposals include solar orbit telescopes positioned at L1 or L2 points to reduce noise and improve infrared resolution, though thermal protection is a significant design challenge. Without advanced shielding, instrument structures would vaporize in similar conditions to those found near K2-141b itself. Even with these innovations, all observational data comes from analysis of light from the planet. Photons travel 201 light-years, pass through molten rock vapor, and reach detectors cooled to -266 degrees Celsius. Measurements are interpreted to determine surface and atmospheric conditions. Brightness fluctuations observed through telescopes are interpreted as vaporization of surface material, providing insight into the planet's thermal and geological activity. Observational data indicate that K2-141b is thermally and geologically active, with surface material vaporizing and contributing to mass loss. Ongoing studies aim to quantify the rate of surface material loss and estimate the timescales of planetary erosion. Could Earth become a K2-141b? Understanding K2-141b's future is harrowing, but turning the lens toward Earth raises a question with far deeper consequence. Could a planet like ours ever transform into something remotely similar to a lava world? While the extreme outcomes seen on K2-141b involve conditions far beyond anything Earth has experienced, researchers studying planetary evolution have begun using such exoplanets as analogues for runaway atmospheric collapse and geological meltdown scenarios. The evidence points to several pathways, chief among them uncontrolled greenhouse effects, orbital decay, and solar expansion that show our world, under extreme conditions, could experience events that resemble early stages of what K2-141b endures today. Earth's average surface temperature is approximately 15 degrees Celsius. Historical satellite data recorded peaks of 56.7 degrees Celsius in Furnace Creek, California in 1913, confirmed by World Meteorological Organization. Atmospheric CO2 levels currently average 421 parts per million in 2025 by NOAA records. Models from the Potsdam Institute indicate that CO2 concentrations around 1,200 parts per million could trigger rapid atmospheric heating. University of Exeter projections estimate that, under extreme greenhouse conditions, Earth's surface temperatures could reach approximately 460 degrees Celsius over 200 million years. Dr. Colin Goldblatt's research suggests that molten rock could form in equatorial regions if solar energy input increases beyond 1.4 times current levels. Venus provides a reference case. Its surface temperature averages 462 degrees Celsius, with atmospheric pressure 92 bars, comparable to being submerged 900 meters underwater on Earth. Atmospheric composition is dominated by carbon dioxide, about 96.5%, with clouds of sulfuric acid. Venus also has slow retrograde rotation and experiences minimal heat redistribution, leading to some conditions that parallel K2-141b's fixed thermal gradient. NASA's Magellan probe from 1,991,994 detected mountainous regions, particularly Maxwell Montes, that may contain traces of lead sulfide and bismuth sulfide, indicating possible high-temperature metal precipitation processes. While it does not rain molten rock currently, Venus's past may have included magma oceans approximately 4 billion years ago. Dr. Alessandra Mastrobuono Battisti from the Weizmann Institute published in Nature Geoscience that early Venus might have maintained a molten state similar to modern K2-141b for nearly 15 million years post-formation. For Earth to approximate similar conditions, the Sun's energy output would need to increase significantly. Stellar evolution models predict that the Sun will grow brighter by about 10% every 1.1 billion years. In approximately 1 billion years, average Earth's surface temperatures could reach 100 degrees Celsius, evaporating oceans. 1.5 billion years from now, according to a publication from the University of East Anglia, expect a CO2 breakdown cycle resulting in atmospheric destabilization. It's at the 3 to 5 billion year time frame, when the Sun begins entering its red giant phase, that Earth could encounter conditions that exceed 1,500 degrees Celsius, potentially sufficient for crustal melting. During the red giant expansion, the Sun may grow to engulf the orbits of Mercury and Venus, possibly reaching Earth's current distance. Some models from Princeton University indicate that if Earth's orbit expands via tidal interactions, it may escape being fully consumed, but would still experience temperatures above 2,000 degrees Celsius for 30,000 to 50,000 years. During that time, magma seas would dominate the planet's surface, atmospheric silicate vapor would form, and rock precipitation cycles may begin. Winds of the magnitude seen on K2-141b, around 5,000 km per hour, would be unlikely on a future Earth due to lower gravity contrast and slower relative heating dynamics. Earth's gravity is 9.8 meters per square second, while K2-141b, with a mass estimation of about 5.08 times 10 to the power of 24 kilograms, approximately 0.85 times Earth's mass, but smaller radius of about 1.5 Earth radii, yields gravity closer to 22 meters per square second on the surface. This stronger gravitational pull contributes heavily to atmospheric retention and ultra-fast tidal jet streams. While post-red giant Earth may experience winds exceeding 1,000 km per hour, these would still fall short of K2-141b, unless orbital compression or gravitational influence from a nearby stellar body accelerates thermal gradients. The chemistry of a future Earth magma atmosphere would differ as well. K2-141b's vapor plume analysis indicates heavy presence of silicon monoxide, sodium vapor, and inferred traces of potassium and iron remnants. Earth's crust composition would produce similar spectroscopic markers, particularly SiO and Na, but could also contain significant signals from aluminum oxide, magnesium oxide, and rare trace volatiles. Mineralogy models from MIT anticipate that at full surface melting, around 45 kilometers of crust could gradually liquefy, comparable to K2-141b's lava layer hypotheses. Tidal locking, another key component of K2-141b's catastrophic heating, is unlikely for Earth in the near term due to its orbital distance. However, if Earth spirals inward due to solar drag in late-stage stellar evolution, the prospect of partial tidal capture increases. Human technological intervention could slow atmospheric warming, but models indicate that beyond certain geological thresholds, Earth would still undergo extreme thermal and geological changes. Supervolcanic eruptions, increased cosmic radiation exposure, and large asteroid impact events may accelerate crustal destabilization. A 2013 investigation by the University of Manchester estimated that an asteroid at least 100 kilometers in diameter, impacting at velocity exceeding 70 kilometers per second, could melt up to 75% of Earth's crust, momentarily producing atmospheric silicate vapor. However, such collision probability is astronomically low, around 1 inch, 100 million per million years. If Earth enters a sustained molten state due to solar influence, atmospheric vaporization could last tens of thousands of years before orbital shift or stellar absorption ends the phase. ESA's Planetary Evolution Lab estimates mass loss between 2-6 kilograms per second, compared with K2-141b's 395-500 and 25 kilograms per second. Most mass loss is expected during the final stages of solar engulfment. Geological history indicates that around 4.4 billion years ago, the Hadean Earth experienced phases of molten rock oceans during early formation. Carnegie Institution of Science models suggest magma surfaces persisted for approximately 4 million years before cooling to form a solid crust. Mission impossible. Why landing here would kill a probe? Attempting to land a probe on K2-141b is not an engineering challenge. It is a physical impossibility under the current laws of material science. Any probe launched toward K2-141b would be destroyed in less than 2 minutes, with most components failing before even touching the planet's molten surface. To understand why, we must analyze every phase of a hypothetical mission: entry, descent, landing, operational survival, and even orbital observation. Across all stages, failure is absolute and immediate. K2-141b's surface temperatures range between 3,026 degrees Celsius and 3,310 degrees Celsius, exceeding the melting point of nearly every structural material known to modern engineering. Tungsten, one of the most heat-resistant metals on Earth, melts at 3,422 degrees Celsius. Under K2-141b's environmental conditions, it begins thermal degradation within 8 seconds. Data supported by material fatigue tests by the Centre National d'Études Spatiales, or CNES, in 2024. Titanium alloys, typically used in the shells of Mars rovers and SpaceX's Starship heat shield segments, fail after under 10 seconds, and ceramics fracture between 95, 100, and 20 seconds due to thermal shock compounded by rapid pressure fluctuations. The planet endures supersonic winds exceeding 5,100 kilometers per hour, which are not based in air but in rock vapor, primarily silicon monoxide, sodium, calcium oxide, and magnesium vapor, released from molten oceans, reaching estimated depths of 40-60 kilometers. These winds carry abrasive molten particulate matter, traveling at speeds faster than rifle bullets. A 2024 ETH Zurich simulation using Direct Simulation Monte Carlo, or DSMC modeling, calculated expected frictional erosion of 1.1 millimeters per second on tungsten carbide surfaces. This would completely strip a lander's structural integrity within 90 seconds. Orbital radiation is even more severe. K2-141b orbits its host star at 0.00716 AU, meaning it receives nearly 7,000 times the solar flux of Earth, estimated at 9,350,000 m². Radiation exposure exceeds 500,000 Gray in less than 3 minutes, where 1,000 Gray is lethal to unshielded electronics. Even the Parker Solar Probe, built to survive temperatures of 1,377 degrees Celsius near our Sun, would deteriorate instantly here. Its carbon-carbon composite shields would chemically react with rock vapor, becoming unstable at 2,900 degrees Celsius. According to NASA's Extreme Systems report in 2023, K2-141b surpasses the probe's tested durability by a factor of at least 2.1 times. Descent systems are non-functional. Typical atmospheric braking methods used on Mars, such as supersonic parachutes tested at 1,500 kilometers per hour and is less than 300 degrees Celsius, are inapplicable. There is no stable air, only mineral gas. Retro thrusters cannot operate effectively in such low-density vapor, and any liquid propellant would boil instantly. ESA's Exo-Boundary program indicated that hydrazine-based landing systems would systematically explode from spontaneous decomposition within 9-11 seconds of exposure. Mechanical stabilization mechanisms like gyroscopic balancing, fail too. Rock vapor storms create pressure oscillations between 5 and 70 bars within 40-60 seconds. For perspective, Earth's sea level pressure is 1 bar, and NASA's Perseverance rover was designed for pressures as low as 0.007 bars on Mars. Venus landers, such as Venera 13 inches 1981, endured 92 bars at 465 degrees Celsius for 127 minutes, but even that environment is gentle compared to K2141b. At 3000 degrees Celsius, with dynamic high-pressure rock vapor, the lander would experience surface pitting at 79 millijoules per micrometer impact energy, sufficient to open structural cracks rapidly. Once gas penetrates, internal overheating occurs at rates exceeding 3.5 megawatts per square meter. The landing itself would be impossible. Impact velocity would exceed 2,500 meters per second with no atmospheric drag. Even if powered descent reduces this, there are lava oceans rather than solid ground. Depth models from 2024 adaptive tomography suggest an average molten layer of 45 kilometers, consisting of basaltic and ultramafic lava heated beyond terrestrial viscosity limits. Contact would cause instantaneous liquefaction of any probe's legs, followed by disintegration from thermal conduction, modeled at 20.4 megawatts per square meter. Even hovering does not solve survival issues. Researchers from the Korea Advanced Institute of Space Materials proposed magnetic levitation using superconductive quantum shielding, but running such a system would require at least 9 terawatts of power, equivalent to Earth's total energy consumption for over 1 hour. Additionally, superconductors cease functioning at temperatures above 200 degrees Celsius. K2141b's ambient is 3,100 degrees Celsius, making magnetic levitation non-viable. Orbital observation is dangerous. At 5,000 kilometers above the surface, satellites would encounter vapor ejecta from thermal updrafts. ESA's atmospheric plume mapping suggests that rock and metal plasma jets reach altitudes of up to 8,200 kilometers. Any orbit lower than 9,000 kilometers would intersect ejecta trails, causing hypervelocity impact fragmentation. Even above that, exposure to stellar radiation would degrade exposure shielding at rates 10 times faster than current low Earth orbit satellite erosion rates. Communication delays further complicate mission planning. Any command takes 402 years round trip, making real-time control impossible. A lander vaporizing in under 2 minutes would cease all telemetry long before any observation of failure reached Earth. Based on modeling from the 2024 International Conference on Deep Space Telemetry, the lander's final signal would be received on Earth around the year 2426, meaning humanity would learn about failure centuries after it occurred. Cooling systems fail too. A continuous presence on the surface would require cryogenic liquid nitrogen cooling at 3.6 gigatons per hour, surpassing the total annual global nitrogen production by a factor of 2,500 times. Insulation would need to exceed the thermal resistance of aerogel, currently at 0.017 W mK, by at least 140 times, which is not feasible using known materials. Even theoretical materials struggle. Quantum phase stabilized composites discussed at the 2024 Geneva Extreme Habitat Symposium, predicted to withstand up to 4,500 degrees Celsius, require containment in vacuum chambers and magnetic stabilization fields, not physical planetary operation. Alloy X209HT, proposed by CERN and constructed with hafnium carbon nanoparticles, theoretically resists 4,000 degrees Celsius, but crumbles under wind speeds is greater than 1,000 kilometers per hour. K2141Bs exceed 5,100 kilometers per hour. Dr. Amara Vekic, ESA Forward Environment Panel, stated, "We might be able to land on the Sun with proper protection before we could land safely on K2-141b. The Sun's outer photosphere is approximately 600 degrees Celsius cooler than K2-141b's surface. No mission plans exist for near-surface solar landing, highlighting the extreme thermal and material conditions on K2-141b. Current technology cannot enable a probe to survive landing on K2-141b under known physical conditions." 2024 reveals a planet in overdrive. Just when scientists believed they had reached the limits of what could be known and endured about K2-141b, 2024 eliminated any remaining sense of stability surrounding this infernal planet. Updated readings from the James Webb Space Telescope, combined with spectral recalibrations using ground stations in La Palma, the Atacama Desert, and Mauna Kea, redefined what we understand about extreme exoplanet physics. Instead of settling into the terrifying numbers previously established, K2-141b appears to be worsening, intensifying, becoming more volatile, almost as if the planet itself is accelerating toward cosmological disintegration. The new models reveal that K2-141b's surface temperatures may now reach up to 3,730 degrees Celsius, an unprecedented increase by approximately 430 degrees Celsius compared to measurements taken in 2021. Based on comparative thermal analysis conducted by the University of Toronto Astrophysics Department in 2024, this suggests that the planet is actively heating, not due to internal geological mechanisms, but because of stellar intensification from its host star, K2-141, which is believed to be increasing its luminosity by about 1.9% per decade. This trend aligns with data from the Gaia DR3 dataset, indicating the star is entering a premature late-life phase, estimated to reach unstable energy fluctuations in fewer than 85 million years, a timescale considered alarmingly short for stellar evolution. New convection models, calculated using adaptive AI simulations run at the European Southern Observatory, indicate that wind speeds could now exceed 6,200 km per hour, nearly 20% faster than previously estimated. The most shocking revision concerns the chemical composition of the atmosphere. Earlier assumptions focused primarily on sodium, silicon monoxide, and trace magnesium, but 2024 spectral deconvolution detected vaporized titanium, zirconium, and even vanadium dioxide, substances never before observed in gaseous form on any planetary body. These findings suggest that not only rocks but raw metals are sublimating into the atmosphere, evidence that the upper mantle may now be undergoing superheating beyond predicted planetary tolerance ranges. The detection of titanium vapor marks a first in exoplanet research. When replicated in laboratory plasma chambers at IRSTI Lyon, titanium vapor combustion reached energy release peaks of up to 167,000 joules per cubic meter, comparable to a military-grade detonation every 14 seconds per square kilometer. More distressing is the behavior of the planet's molten rock ocean. Previous depth estimates averaged 40-60 kilometers, but using updated interferometric simulations, researchers deduced the magma layers are deepening, possibly reaching 83 kilometers in some equatorial regions, as hot mantle materials expand and sink under relentless stellar bombardment. Instead of stabilizing K2-141b's geology is becoming more liquid and less structurally coherent, amplifying volatile resurfacing. A time-lapse model from ETH Zurich using differential thermal decay rates predicts that at current intensification levels, the molten ocean may engulf most surface protrusions within 2.7 million years, effectively transforming the planet into a molten sphere with no solid landmass. JWST's near-spec instrument, tasked with analyzing thermal gradients across the planetary dayside, recorded peak irradiance fluxes exceeding 10,400 W/m², compared to the previously accepted 9,350 W/m². Meanwhile, night-side temperatures, once believed to stabilize below -200°C, were measured at around -172°C, suggesting atmospheric convection is redistributing heat more aggressively, further increasing the speed at which molten material cycles from day to night. One of the most alarming updates concerns atmospheric mass loss rate. Earlier models suggested 32,000 kilograms per second of rock steam escaped the planet. Revised calculations now estimate 56,000 kilograms per second, suggesting that K2-141b is evaporating more rapidly than initially predicted. That equals nearly 4 Olympic-sized swimming pools of molten rock lost every second, injected into space in expanding mineral plumes. If this rate continues, the planet could lose up to 1.3% of its total mass every 10 million years, evidence that it may be on track to complete material dissolution before being consumed by its star. Further distress comes from the detection of ionized silicon plasma jets, accelerating at 5.9 times 10 to the power of 5 grams force through magnetic interaction. These jets were observed in a 2024 high-resolution Doppler shift analysis, measuring velocity transitions up to 39.4 kilometers per second, which is not only physically destructive, but implies new forms of electromagnetic instability forming in the upper atmosphere. Space weather monitors from the Copenhagen Institute of Interstellar Plasma Dynamics confirm the jets induce magnetic turbulence exceeding 5,000 nanoteslas, an anomaly considering Earth experiences geomagnetic storms at to 500 nanoteslas during a significant solar event. Backing these figures, JWST's MIRI detector registered traces of vaporized thorium and uranium isotopes, prompting speculation that radioactive minerals from deep crustal reserves are now entering the vaporized atmospheric cycle. If the concentration is increasing, the planet's internal energy source may be shifting, not solely powered by stellar absorption, but also by accelerated nuclear decay triggered under extreme pressure and heat. The geological supercompression model, proposed by Professor Luca Venegas of Harvard in 2024, indicates that deep mantle compression at is greater than 450 gigapascals could force radioactive excitation of heavy elements, adding yet another energy source to an already catastrophic environmental system. K2-141b's orbital mechanics were also updated. Once believed stable, the latest dynamic models indicate orbital decay of 0.000075% per year, meaning the planet is slowly spiraling toward its star. Using integrated orbital decay projections presented at the 2024 International Exoplanet Congress, the collision or complete disintegration scenario is estimated to occur within 23 to 28 million years, which is remarkably soon in cosmological time. Furthermore, the silicate glass atmospheric layer, previously thought to act as a partial reflective barrier, has been reclassified as an active plasma mirror due to high infrared reflectivity. This reflectivity was measured at 64.2%, meaning more energy is trapped within the planet's thermosphere than released into space, further increasing surface heating, a positive feedback loop resembling a runaway greenhouse, but with molten rock instead of water vapor. A supplementary discovery in late 2024 adds another layer of extremity. Peak winds reaching 6,800 kilometers per hour in equatorial zones during thermal upbursts. At these speeds, energy impact upon exposed material exceeds 118,000 joules per cm squared, enough to pulverize reinforced tungsten carbide within 0.38 seconds. A new hazard classification, hyperdynamic thermal vaporization, was introduced by the International Planetary Hazard Registry, specifically due to K2-141b, a classification currently assigned to no other known planet. The updated data indicate that K2-141b is undergoing increasing surface heating, mass loss, and atmospheric instability, and models project significant structural and thermal evolution as it continues orbiting close to its star. The 2024 ESA Extreme World Assessment Committee concluded that K2-141b exhibits accelerating environmental changes beyond previous models, rather than stabilizing at previously estimated extremes. If these trends continue, future observations may show substantial mass loss and altered surface conditions, potentially rendering the planet increasingly difficult to detect over time. Deadlier worlds loom, planets worse than K2-141b. The haunting escalation seen in K2-141b's latest 2024 data would be enough to define it as a planetary horror beyond anything our technological eyes have witnessed. Yet the most chilling revelation in modern exoplanet research is that it may not be the worst. As telescopes refine their detection thresholds and space missions improve spectral sensitivity, scientists are uncovering even more violent worlds, each redefining extremity and expanding the boundaries of planetary survival physics. A leading example is HD 189733b, a gas giant located approximately 64.5 light-years away in the constellation Vulpecula, infamous for conditions that surpass atmospheric violence modelled on K2-141b. The planet's skies are believed to be filled with silicate particles, and winds reach 8,700 km per hour over Mach 7, surpassing speeds recorded on K2-141b's recent readings. This world exhibits one of the most visually striking phenomena: sideways rain composed of molten glass due to intensely heated atmospheric layers where condensed silicon dioxide crystals form and then are violently thrust by lateral winds. Simulations conducted at the University of Exeter's Exoplanet Climate Laboratory in 2023 estimate that any object exposed on HD 189733b's dayside would disintegrate in less than 3 seconds, not from melting, but from being shredded through abrasive, vaporized glass propelled at hypersonic speeds. Another global hazard contender is WASP 121b, located about 850 light-years from Earth. Classified as an ultra-hot Jupiter, it orbits its host star so closely that the upper atmosphere reaches around 2,700 degrees Celsius, allowing iron and magnesium to vaporize, then rise and condense into stratified clouds before being ejected into space. JWST observations from April 2024 reported atmospheric expansion beyond gravitational containment, with mass loss exceeding 1.2 times 10 to the power of 14 grams per year, approximately 6 times higher than K2-141b. Equally startling is Corot 7b, which shares many characteristics with K2-141b, but presents unique deviations. Only 489 light-years away, it orbits its star at just 0.017 AU, maintaining 144 times the solar irradiation Earth receives. Its surface temperature is estimated at 1,980 degrees Celsius on the day side, though slightly cooler than K2-141b. However, the disturbing factor lies beneath its surface density: 7.5 grams per cubic centimeter, nearly 3.2 times Earth's average, implying a predominantly metallic core and possibly a complete absence of any liquid phase boundary, rendering internal heat transfer far more violent. The ESA Korot mission concluded that seismic disruption on Korot 7b occurs hourly, producing tectonic eruptions ejecting up to 4 cubic kilometers of magma per event, exceeding typical terrestrial volcanic output. One more extreme case is Kelt 9b. This giant planet orbits a 10,000 K A-type star and remains the hottest exoplanet ever measured. Recorded dayside temperatures exceed 4,300 degrees Celsius, hotter than the surface of some stars, such as red dwarfs like TRAPPIST-1. According to NASA's 2024 thermal infrared data, its atmospheric layers cannot exist in standard chemical states. Molecules are torn apart into individual atoms under constant photodissociation, meaning normal weather patterns physically cannot form. The atmosphere primarily consists of atomic iron, ionized calcium, and strip-mined hydrogen, with no evidence of stable clouds or thermal inversion zones. Modeling conducted by MIT's Computational Stellar Research Group suggests any solid probe or high-tensile material would vaporize at 1,200 kilometers altitude before atmospheric entry, which is higher than where Earth's ISS orbits. One candidate is the exoplanet OGLETR-56b, orbiting just 0.023 AU from its host star, where atmospheric pressures exceed 200 bars. High metal analysis indicates gold and platinum vapor signatures, suggesting internal temperatures sufficient to liquefy precious metals. The intense dynamics of its Roche limit proximity indicate a likely complete tidal breakdown within 12 million years, shorter than projections for K2-141b's decay. Turbulence modeling by the Shanghai Planetary Dissolution Institute in 2025 predicts that OGLETR-56b could experience planetary fragmentation events, possibly observable as micro-impact clusters by JWST by 2031. Janssen, also known as 55 Cancri E, located 41 light-years away, displays surface temperatures approaching 1,900 degrees Celsius and an atmospheric composition potentially rich in carbon-based minerals, including high-form diamond structures under extreme compression. In 2023, the Max Planck Institute published data suggesting visible flickering in its thermal emissions, possibly indicating real-time tectonic collapse and reformation processes. A hypothesis proposed by planetary geologist Sarah Major of Cambridge in 2024 suggests that Janssen's mantle layers may undergo up to 800 earthquake-like structural shifts per day, which would make its crust mechanically unstable to any form of probe landing. Astronomers examining stars like Kepler 7a, HD 63433, and TOI 849 report that K2-141b, like planets, may exist in high-temperature states with potential for extensive material loss, producing orbital mineral debris detectable long after core disintegration. A paper presented at the July 2024 Paris Deep Space Climate Symposium introduced the concept of thermal-assisted planetary mortality, classifying planets based on star proximity-induced material loss. Some worlds exhibit atmospheres that merge directly into stellar plasma fields, such as WASP-12b, whose orbit decays by 29 milliseconds per year, generating tidal stress sufficient to distort its shape into a prolate ellipsoid. Mass loss rates for WASP-12b exceed 1 × 10 to the power of 15 grams year, which could result in full absorption by its star within 10 million years. K2-141b is classified as a representative of a new category of terminal stage exoplanets. These Type U, or unstable class worlds, are characterized by thermal acceleration, with environmental forces intensifying over time rather than stabilizing. At the 2024 European Space Agency Strategic Planetary Assessment, researchers introduced the term catastrophic trajectory progression to describe planets experiencing accelerating environmental deterioration. In 2024, the Federation of Exoplanetary Research Modeling Unit published a percentage breakdown of known extreme planets with high-risk material loss or orbital instability over the next 100 million years. Results indicated that 41% of all ultra-hot Jupiters are projected to dissolve or merge with their stars. 22% of known lava planets, including K2141b, have unstable orbital decay rates beyond thermal equilibrium. 6.8% are undergoing core detachment, a process incompletely understood, and 1.3% demonstrate signs of potential stabilization, primarily those in slightly cooler orbits. K2141b exhibits environmental conditions that fall within a spectrum of high temperature, high mass loss exoplanets. Observations of planets such as Kelt 9b demonstrate that higher temperature extremes and structural instability exist beyond those measured on K2141b. Planned interferometric probes under the LUVOIR and HABEX mission frameworks will allow scientists to observe exoplanets with extreme environmental conditions, including rapid phase transitions between liquid and plasma and the presence of high-energy materials not previously detected in planetary atmospheres or surfaces. Exoplanet research teams have issued internal advisories highlighting the need for preparation when observing planets with extreme environmental conditions, including high temperatures, rapid mass loss, and unstable atmospheric or surface dynamics. K2141b warned us, the next planets will push our understanding of survival and destruction even further.